This module introduces the Avaya Session Border Controller for Enterprise, or ASBCE, and provides a foundation for the rest of the course. Let's review the objectives to understand what will be presented in this module. At the end of this module, you should be able to define Session Border Controller and its role in the network, explain the security elements provided by the ASBCE, describe some of the ASBCE features or capabilities with IP Office, and describe some of the new features in the ASBCE 8.0. To understand the term Session Border Controller, let's take each word separately to describe its functionality. A session is communication between two or more parties. In a telecommunications network, signaling is required to initiate, maintain, change, and finally break down the session. The session includes the call media streams, such as audio, video, data, call control signaling messages, and the call information for billing, tracking, legal compliance, etc. Keep in mind that SIP is Session Initiation Protocol, and it is the signaling protocol that the ASBCE is designed to use. SIP is another signaling method in the long evolution of telecommunications, such as H.323, System 7, and others. The border is the demarcation point between one part of a network and another. In this diagram, it is the edge of a corporate or trusted network that separates the public or untrusted network. Since information flows over this border, it is here that the work of the ASBCE takes place. Frequently, the ASBCE will be positioned in the demilitarized zone, or DMZ, and behind the firewalls. The purpose of a DMZ is to add an additional layer of security to an organization's local area network, or LAN. An external attacker only has access to equipment in the DMZ rather than any other part of the internal network. The servers most vulnerable to attack are those that provide services to users outside of the LAN, such as email, web server, VPN, and DNS servers, which are placed in this isolated subnet. This protects the inner or trusted network even if an intruder successfully attacks any of these servers. Also, it is understood that not all threats come from the outside and that measures must be taken to prevent, detect, and eliminate internal risks. The Session Border Controller is one element in an overall enterprise security program and does not replace the corporate data firewall. The controller modifies, masks, or redirects data streams as they pass from one part of a network to another. It analyzes signaling and media streams to route the traffic while applying policies to it. In the graphic, the IP Office communicates with the ASBCE over its private network. The ASBCE, in turn, communicates with the carrier or the remote worker or user over its public interface. Therefore, the ASBCE influences data passing in either direction, outwards to the untrusted network or inwards to the trusted enterprise network. The current industry best practice for securing the enterprise network edge for voice-over IP SIP-based communications is implementation of an ASBCE at the edge of the enterprise network. As a part of the corporate network, the ASBCE offers many benefits. The first benefit is the reduction in cost. With the advent of voice-over IP, it is possible to combine voice and data communications over a unified data infrastructure. This combination reduces cost. In addition, SIP allows an enterprise to eliminate costly private PRI trunking and instead use existing public internet connections. Better management of the network is another benefit. The network is easier to manage since the ASBCE handles TCP, UDP conversion, and codec conversion. Many changes can be made with a software configuration update. Finally, remote users may also be handled as on-net users when using their laptop, soft phone, or mobile smartphones. Keep in mind that easier management also reduces cost. The ASBCE then becomes a key component in a SIP trunking and remote users network because it performs critical roles, including security, routing, quality of service, transcoding and transrating, and SIP translations. You'll learn more about these critical roles throughout this training. Now, we'll move to the security elements provided by the ASBCE. Security is paramount to every business and their partners, employees, and customers. Failure to provide adequate security can result in exposure or loss of information, loss of time, money, or capital resources, legal exposure, liability, loss of credibility, trust, or market share, and lower performance, standard, achievement, or certificate ratings. These losses can be mitigated with a consistently applied and well-designed security policy and systems that support secure enterprise communications. The ASBCE is one of the systems that provide that security. Here are 4 everyday examples of general security vulnerabilities that must be addressed by a security plan and the ASBCE. First, confidentiality in both data and communications is perhaps the highest security priority. Second, systems must be available to perform as designed whenever needed. However, sometimes a directed attack can interrupt or suspend services of a host by flooding it with communication requests so that its resources are consumed and it cannot provide the intended service. Third, authentication methods must ensure that system users are who they claim to be. And lastly, preventing data modification ensures the integrity of the enterprise communications and complements the confidentiality plan. Let's look at each of these requirements in more detail. First, confidentiality or privacy of communications and data is the highest priority for security. Interception of communications and data or attacks include eavesdropping on the media stream, the communications payload. For example, an attacker listening in on the conversation. Eavesdropping reconnaissance on signaling traffic to determine who calls whom, the numbers dialed, and time and date of call. Attacking a VoIP endpoint, gaining control of the device, and stealing confidential business data. Voice and data communications are business-critical resources. Some traditional phone systems have a 100-plus year track record of near-total availability. That is, whenever you lift the receiver, you always have dial tone and can make calls. There might have been times when the system was not available, but if you did not need the system at that moment, then the system is considered available. Any attacks that tie up VoIP resources, making the system unavailable even for seconds, are attacks against availability. Denial of service and distributed denial of service attacks are typically executed by one or more people who interrupt or suspend services of a host by flooding it with communication requests, so that its resources are consumed and it cannot provide the intended service. A flood of information and/or requests to a single network adapter affects every computer in the network. Many creative fuzzing techniques uncover security vulnerabilities that make denial of service attacks possible. Fuzzing is a software testing technique used to discover coding errors and security loopholes in software, operating systems, or networks by inputting massive amounts of random, unexpected, or invalid data called fuzz to the system in an attempt to make it crash. Stealth attacks are essentially lower-frequency DOS attacks. For example, your phone could ring every 5 minutes. Although this is not your traditional DOS attack that brings down the entire system, it is extremely annoying and can impact your ability to work. An example of an authentication attack occurs in toll fraud. Toll means a call is made to a destination beyond the local area, which is charged above the local or flat rate to the calling party. Often, a user must be authorized to dial long distance through the permissions associated with the device login, If hackers intercept dial patterns to retrieve access codes, then the hackers are free to place unauthorized and expensive calls. Hackers are unable to get these access codes with an ASBCE. Integrity prevents the modification of data or communications and normally goes hand in hand with confidentiality. Instead of gaining control of the VoIP endpoint and stealing confidential data, the attacker modifies or deletes the data without the user's knowledge. The diagram shows an example of an integrity attack through interception and modification. The hacker intercepts the information being exchanged, modifies it, and sends it to the destination. Unfortunately, the calling party is unaware of the change in data. For example, if caller ID data is modified, an attacker can pose as a financial institution, credit bureau, taxing or regulatory authority, law enforcement, or emergency services. Misrepresentation plays a key role in most phishing-type attacks. With the multi-device access feature, a user can access calls on multiple devices of various capabilities. However, all the devices use the same number. All the user devices ring for an incoming call, and the user answers with the chosen device or a paired mobile device. After the call is answered, the remaining devices stop ringing. If the user wishes to use a device with better capability, the user can join an existing call using that device. Topology hiding provides values privacy to the network. This feature allows you to change key SIP message parameters to hide or mask how your enterprise network appears to an unauthorized or malicious user. It hides the trusted network from the outside or untrusted network and establishes the demarcation between them. The ASBCE can also encrypt SIP signaling and media packets. The remote user configuration gives remotely located SIP users access to the internal enterprise UC or Unified Communication Network by implementing comprehensive UC security features. These features include sophisticated firewall NAT traversal, encryption, user authentication, and session and endpoint call policy enforcement. In addition, ASBCE supports components in the enterprise with both IPv4 and IPv6 addresses. The far-end remote user, call server, and trunk server can support a mixed IPv6 and IPv4 address family for SIP. We'll talk more about the support of remote users later in this training. Deployments on a virtualized hardware are supported. If deploying on VMware, the packages are vAppliance ready. Amazon Web Services and Linux kernel-based virtual machine are also possible. See the Deploying Avaya Session Border Controller for Enterprise in Virtualized Environment document for more information on virtualization. Interoperability is an important function of the ASBCE because not all VoIP solutions are created in the same way. The ASBCE enables different networks to communicate by providing external IP addresses that are substituted with internal IP addresses. This process provides additional security and is called NAT, or Network Address Translation. The SIP header messages can be manipulated in order to adjust or normalize different SIP implementations. National security in most countries has specific regulatory requirements of communication equipment. To support these requirements, the ASBCE supports emergency calls prioritization, such as E911 phone calls, compliance with communication regulations, and law enforcement agencies' enablement to intercept telecommunications, commonly known as wiretapping. In support of the small to medium-sized market, or SME, Avaya Session Border Controller also provides enterprise-class SIP security for SME, price and performance optimization, and superior ease of data and feature management. If you are using IP Office 8.1 with FP1 or Feature Pack 1, you also receive a graphic user interface-based EMS and SIP normalization tool and an environment that is scalable to large SME environments. With the addition of advanced services in IP Office 9.0 and higher, you also benefit from VPN-less SIP remote user protection and signaling and media encryption. Therefore, the ASBCE is targeted for SME implementations. To use a feature, you must ensure that the license file that you upload to WebLM has the appropriate licenses for the feature. You cannot configure or use a feature if the correct license for that feature is not present in the license file. Take a moment to review this information, and when you are ready, click the Next button to continue. ASBCE is available in two versions: Advanced Services and Standard Services. This is a list of some of the ASBCE functions and features included within Standard Services. Advanced Services includes all of the functionality in Standard Services, plus Remote Worker to support the VPN-less mobile workspace, encryption and media replication to a recording device. Remote Worker Security starts with the use of TLS for signaling and SRTP encryption for the media, depending on the device implemented. A la carte licenses, media replication, support for stun, turn, WebRTC. Video services, Scopia SIP clients, support for Scopia XT clients as remote workers, and support for BFCP, Binary Flow Control Protocol, Far-End Camera Control, FECC, Remote Worker, validate and securely support remote mobile users for extension of IP Office UC services, signal-only encryption, transcoding service, and finally, CES service. Note that since the advanced license is required for SRTP support and remote worker support, it is recommended for an IP Office deployment. Some of the important features available with the ASBCE Release 8.0 for the mid-market solution are new platform support, simplified deployment, backup and restore improvement, deployment via command line application programming interface, API, upgrade and rollback enhancements, EMS graphic user interface, GUI changes, simplified certificate management, simplified and secure certificate installation, WebLM certificates, synchronization of certificates on HA pairs, multi-tenancy enhancements, improved system outage notifications, improved real-time data changes without server restarts, and improvements for Equinox solution. The virtual platform lineup includes support for VMware versions 6.5 and 6.7. VMware version 5.5 is no longer supported with 8.0. The available VM OVA profiles have been streamlined. Where there used to be small, medium, and large, now we have either ASBCE or EMS. Other platforms such as Nutanix, KVM, and Amazon Web Services are also supported with ASBCE version 8.0. The ASBCE 8.0 includes a feature called Simplified Deployment that encompasses several areas of the platform. Among these are backup and restore functionalities. In previous releases, it was not possible to back up or restore a specific ASBCE on an EMS where multiple ASBCEs were installed. Now, with this version, it is no longer necessary for all ASBCEs to be online in order to take a backup or snapshot. Configurable snapshots taken of an ASBCE that is registered with one EMS can be restored to another ASBCE associated with an EMS different from that it was created. Note that the same build version, number of NICs, and device type are required when restoring a backup. All deployment types are now covered to better facilitate platform replacement scenarios. Part of the simplified deployment feature includes a command line application programming interface (API) to facilitate ASBCE configuration. Prior to this release, the EMS GUI was the only way to configure an ASBCE. This API facilitates platform pre-staging. For example, in a scenario where a customer can use a master lab setup to generate configurable snapshots, which are then used to stage new instances. They can then use the command line API to customize the configuration as needed for a specific deployment. The customer can even have multiple master lab systems for different service levels, such as gold, silver, or bronze, then replicating and customizing them as needed. The API provides the means to change the configuration of the most common configurable items, such as network configuration, SIP servers, WebLM servers, amongst others. It also provides the means of changing the EMS IP address and enabling and disabling the ASBCE data interfaces via command line. Part of the simplified deployment feature, address the issue of complex and lengthy upgrades. PreCheck is designed to be run at any time, even outside of a maintenance window, and is there to help plan upgrade activities in case a problem is found. It may not find every problem, but will give a good idea with respect to upgrade expectations, disk space, platform, release, etc. The earlier versions of the ASBCE have to be at least in the either 7.1.x or version 7.2.2 before they can be upgraded to version 8.0. Please review the release notes for version 8.0 or the version that you are going to upgrade to first. For example, if you're going to be upgrading to version 8.0, please refer to the document Upgrading the Avaya Session Border Controller for Enterprise Release 8.0. The ASBCE contains numerous improvements in the graphic user interface of the Element Management System, EMS. One of the most important changes include the ability to manage each of the devices, the EMS and the ASBCE, separately. A new device selection pull-down option is now available in the upper left of the EMS GUI. This is used to select the device on which the GUI operation is going to take into effect. The EMS only or the ASBCE HA pair can be selected. The navigation menu will change according to the device selected. This allows the separation of the global data from the device-specific data. This implies that the changes made to the selected device will not be made to the other devices. The global profiles has been renamed or changed to configuration profiles and is available under the ASBCE or ASBCE HA drop-down menu. The server configuration, which was under global profiles, is now available under services and in SIP servers. Other EMS GUI changes include the moving of the radius configuration from global parameters to under System Administration, AAA Server. The SIP server configuration is now available under Services. The new LDAP server configuration has been added under Services, and PPM mapping has moved from PPM Services to under DMZ Services. In prior ASBCE releases, it was necessary to run cert install and cert sync commands on the ASBCE when installing and managing certificates. In 8.0, certificates can be completely installed from the EMS, even on HA deployments. Due to the separation of the global data and device-specific data, certificate management will depend on the device selected. If a certificate needs to be installed on a different device, the installation process has to be repeated for that device. If the device is a HA pair, the certificates will be synchronized automatically. The cert sync command should no longer be used. In the next couple of screens, we will see that there now exists a GUI button in the certification window if manual synchronization is required. When generating a certificate, the private key remains local on that device and cannot be transferred via the GUI. The administrator can, however, use SFTP to securely transfer the key to another device. In previous releases, a manual process was sometimes needed when installing a certificate for a remote web LM server. In 8.0, after configuring a web LM server, the certificate provided by that server can be verified using the Verify Existing Certificate button. If the certificate is not trusted, the admin can choose to trust it. No manual process is necessary. In ASBCE 8.0, certificates are automatically synchronized between servers in a HA pair. However, if there is any issue synchronizing the certificate automatically, an alarm will be raised. In that case, synchronization can be performed manually from the GUI by clicking on the Synchronize to HA Peer button in the Certificates Management window. ASBCE has supported a multi-tenant model for several releases. A multi-tenant model is one where a single ASBCE supports multiple isolated and independent user bases or tenants. In previous releases, any configuration changes for specific tenants often required application restarts in order to apply those changes. This impacted all tenants on the ASBCE, even if the configuration change did not apply to them. Warnings were displayed when editing the GUI configurations, indicating what the impact of the configuration change will be if the configuration change was to be made. Attempting to remove or change a configuration will generate a warning along with the information regarding the impact of the change. Data dependency checks are now in place to prevent, for example, the removal of an IP address that could take out service for one or more tenants. So, in order to delete a certain configuration, if there are other configurations relying on it, they must be removed first. In this release, enhancements were made for approximately 20 different configurable items. There are still a small amount of configurations that requires a restart in order to apply changes. These items will be addressed in future releases. The Microsoft Edge browser does authenticate with a new nonce when authentication is enabled. Configurable nonce expiry time has now been added in the turn server configuration to support this Edge browser limitation. The nonce timer gets refreshed when client authentication is enabled. This still works with other browsers. Unlike SIP sessions, turn capacity is directly linked to compute resource available. Greater capacity at the cost of greater footprint is useful for services expected to provide large scalability, such as a VIA Equinox meeting online. In the ASBCE version 7.2.x, we were limited to 30 media tunnels total. With 8.0, we can now deliver 30 media tunnel per vCPU consumed by the application. For example, with 4 vCPUs, 120 media tunnels are available. We have concluded this module that introduced the ASBCE. You should now be able to define Session Border Controller and its role in the network, explain the security elements provided by the ASBCE, describe some of the ASBCE features or capabilities with IP Office, and describe some of the new features in the ASBCE 8.0. Hello, and welcome to this module that focuses on the IP Office and ASBCE architecture and hardware. Let's review the objectives to understand what will be presented in this module. By the end of this module, you should be able to define the two components of the ASBCE, describe the two ASBCE deployment options, use a diagram to describe an architecture that includes the ASBCE and IP Office, and compare and contrast the servers that can be used for the ASBCE in the small to medium-sized mid-market. Let's start with the two components of the ASBCE. The ASBCE has two components. The first one is the ASBCE itself, which resides at the edge of an enterprise network and serves as an application-aware SIP firewall for securing SIP-based unified communications in and out of the network. ASBCE secures SIP traffic to and from carriers, which is called trunking. It also provides VPN-less support to remote users outside the firewall, as well as advanced functionality, including encryption, media replication for recording, etc. It is part of a fully integrated solution within the Avaya application stack. The Element Management System, or EMS, administers and manages one or more ASBCEs for both standalone servers or high availability, or HA systems. Administrators may use the command line interface or the EMS to manage the ASBCE. Depending on the network size and service requirements, deploy the ASBCE and EMS in one of the following configurations. In the standalone configuration, the ASBCE and EMS are located in the same server. This configuration is commonly known as the all-in-one or standalone configuration. In the multiple server configuration, EMS and ASBCE are deployed on separate servers. These can be deployed virtually or by using hardware supplied by Avaya. Here is an example of a single server configuration. The server with the ASBCE and EMS as co-residents, or all-in-one. Here is another example of the way in which the ASBCE can be deployed in a non-redundant configuration. In this example, the ASBCE and the EMS are installed on two separate servers. Optionally, the EMS can also be installed on two servers. One EMS is configured as the primary and the other as secondary. Diagram 2 illustrates that an EMS server or pair can manage up to 25 non-HA ASBCE servers. High availability deployment. In this example, there are two ASBCE servers with a separate EMS or a pair of EMSs. Note that the HA deployment does require an HA license. Diagram 2 illustrates that an EMS server or a pair of EMS servers can manage up to 12 pairs of high availability ASBCEs. We will review the details of the HA configuration in the next module. Here is a diagram of a standalone deployment. There is not a separate server for the EMS. The ASBCE and EMS are on a Portwell standalone server and provide security for the SIP trunks and the remote workers. Notice that the ASBCE is placed behind a firewall and does not replace a firewall. This solution is for a small business with an ERS or Ethernet routing switch as its network core. It also has IP Office Server Edition with the IP Office IPO 500 version 2 expansion connected to it. In the next module, the high availability architecture will be discussed in more detail. Now that you have a basic understanding of the different architectures in which the ASBCE can be implemented, let's turn our attention to the hardware. The ASBCE 8.x supports many different Dell, HP, and Portwell servers. For detailed information about the servers, refer to the ASBCE 8.x documentation, including deploying Avaya Session Border Controller for Enterprise. The ASBCE servers are fully integrated, user-installed chassis. ASBCE supports the hardware shown here. Take a moment to review this information, and when you are ready, click the Next button to continue. We'll start with the Portwell server because it is often used in the small to medium enterprise market. The Portwell server is the all-in-one server in which the EMS and ASBCE reside on the same server. It is only used for single server deployments. Its capacity and functionality cause it to be used frequently in the ASBCE and IP office configuration. The new Portwell CAD0230 will replace the existing Portwell CAD0208 in the Release 8.x timeframe. The older CAD0208 will continue to be supported for new ASBCE releases throughout the Release 7.x stream, with the newer CAD0230 replacing the CAD0208 as the CAD0208 supply winds down. This gradual plan allows for a smooth transition to the newer platform. Performance and capacities will be the same between the platforms. This table shows how the Portwell compares to other servers often used for the ASBCE and EMS. Notice the Portwell system memory, onboard storage, and dimensions are significantly smaller than the other servers listed. Take a moment to review this information, and when you are ready, click the Next button to continue. Here are the capacities for servers that are typically used for the mid-market. As mentioned previously, the Portwell is suited for small enterprises and the IP office. It is ideal for enterprises that do not require SIP-REC with SIP trunking, Scopia, or transcoding. It also does not support multi-server deployment. The Dell R320 and R330 are also mid-range platforms for the enterprise. They can be used for either separate EMSs or ASBCE applications in a multi-server deployment, or they can also be deployed with both EMS and SBC co-resident in a single server deployment. The HP DL360 is a mid-range platform for the enterprise. This platform has a single CPU, dual power supplies, and hot swap hard drives. It can be used for either separate EMS or ASBCE applications in a multi-server deployment, or it can also be deployed with both EMS and SBC co-resident in a single server deployment. VMware 6.x capacities are measured with 4 CPU and 8 GB of RAM. Allocating more resources will yield higher performance. To calculate calls per second, divide the maximum concurrent sessions by 180 because 3 minutes or 180 seconds is the hold time for the above measurements. To calculate the busy hour call completion, multiply the maximum concurrent sessions by 20. This concludes this module. You should now be able to define the two components of the ASBCE, describe the two ASBCE deployment options, use a diagram to describe an architecture that includes the ASBCE and IP office, and compare and contrast the servers that can be used for the ASBCE in the small to medium-sized mid-market. Take a few minutes to review these objectives. Are you able to perform these objectives now? Welcome to this module that focuses on deployments that include high availability or HA. Here are the objectives for this module. By the end of this module, you should be able to describe the hardware configuration for an ASBCE high availability solution, Summarize how the primary and secondary ASBCEs operate during a failover. State the purpose of each subnet that is often used in an HA deployment. Explain why the GARP protocol is critical during an ASBCE failover. In the high availability or HA configuration, ASBCE servers are deployed in pairs. Each pair has one ASBCE server acting as primary while the other is secondary. Both servers are controlled by a single Avaya Element Management System or EMS device or a replicated EMS pair. One EMS server or a pair of EMS servers in replicated mode can control up to 12 separate pairs of ASBCE servers. Here is a way to implement IP Office with a virtual and ASBCE HA deployment. Notice this environment includes two ASBCEs to provide SIP redundancy. The ASBCEs in a HA environment were configured in active standby mode. Although not shown here, the EMS can be replicated if needed. In that case, EMS is installed on two servers, and one EMS is configured as primary and the other as secondary. If using a single EMS server, that EMS is configured as primary and controls multiple ASBCEs. One EMS server or a pair of EMS servers in replicated mode can control up to 12 separate pairs of SBC servers. From Release 7.1, ASBCE supports an EMS HA active/active configuration. If the EMS hardware fails, the system will not be out of service. The system can switch to the other EMS in the HA pair without manual intervention. A VMware host with a Type 1 hypervisor, such as VMware's ESXi, connects via NIC teaming to both at the core network. The host configuration provides virtual machine redundancy. The advantage of this deployment is to keep IP Office Server Edition primary with Avaya 1X portal alive, even when one switch or server fails. Notice the IP Office is in a high availability configuration as well. In addition, the ASBCE can be deployed as a pair either in the Enterprise DMZ or Core. It can also be deployed in a geographically dispersed configuration, where each ASBCE resides in a separate physical facility. In either configuration, ASBCE HA pairs can be deployed in an enterprise in a parallel mode configuration. In the parallel configuration, the signaling packets are routed generally to the primary SBC. Even if traffic is accidentally routed to the secondary ASBCE, the secondary ASBCE will drop it. Since the secondary ASBCE's ports are disabled, the secondary ASBCE, which is on standby, ignores the packets. The active or primary ASBCE performs all data processing. The interface ports on the standby ASBCE do not process any traffic. In an HA deployment, the management interfaces of the EMSs have different IP addresses, but the A1 and B1 interfaces on the ASBCEs have the same IP address. On failover, the A1 and B1 interfaces addresses do not change. In addition, the standby ASBCE advertises the new MAC or Media Access Control address as the Layer 2 address for the secondary ASBCE. The ASBCE devices are synchronized through the heartbeat on the dedicated interfaces, and both ASBCE devices are in continuous communication with the Avaya EMS. In failover, the standby SBC broadcasts its new MAC to the network as a GARP message, so the network will now flow the message to this ASBCE server. The original active ASBCE will disable its port. When the EMS detects a failure on the active ASBCE, The active or primary SBC's A1 and B1 interface ports are both automatically disabled. The ports of the standby or secondary ASBCE are enabled. Failure detection and operational transfer occur without dropping packets or adding any significant amount of latency into the data paths. The EMS reports the change in status to the EMS for action by the system administrator. Although the ASBCE servers are duplicated in a high availability configuration, the EMS servers can also be replicated. EMS replication gives an enterprise the option of deploying two Avaya EMS servers to ensure uninterrupted network monitoring and control. EMS data is replicated between the servers repeatedly as determined by user-defined fields on the EMS GUI interface. These servers can be located in the same facility or in different geographic locations. ASBCE 7.1 and later support EMS HA active configuration. When one EMS fails, the other EMS is usable without any manual intervention or downtime. Now that you understand some general information about the high availability deployment, let's discuss some considerations that must be reflected in an HA architecture. These considerations include subnets, the GARP protocol, and licenses. We'll start with subnets. The typical high availability configuration requires 3 networks or subnets. Although private or public side can be assigned to any interface, A1, A2, B1, B2, in this presentation, we will use A1 as private, B1 as public. As a matter of fact, most users adopt this practice. The private or trusted network for the A1 interface is shown by the red lines. The public or untrusted network for the B1 interface is shown by the blue lines. The management network for the M1 interface that is dedicated to EMS to ASBCE traffic is shown by the yellow lines. The green line for M2 to M2 is for the duplication link between the two ASBCE servers. Note, all servers ship with preloaded software. ASBCE high availability also requires gratuitous address resolution protocol (GARP) support on the connected network elements. When the primary ASBCE fails, the secondary ASBCE broadcasts a GARP message to announce that the secondary ASBCE is now receiving requests. The new active device sends a GARP message to update the ARP or address resolution protocol tables of the neighboring HA device. This new active device begins receiving traffic. The GARP message announces that a new MAC address is associated with the ASBCE IP address. Devices that do not support GARP must be on a different subnet with a GARP-aware router or L3 switch to avoid direct communication. Devices that do not support GARP continue sending calls to the original primary ASBCE. For example, to handle GARP, branch gateways, MedPro, Crossfire, and some PBXs or IVRs must be deployed in a different network from the ASBCE with a router or L3 switch. If you do not put the ASBCE interfaces on a different subnet after failover, active calls have a one-way audio. The last consideration is about the high availability license. To use an ASBCE feature, ensure that the license file that you upload to WebLM has the appropriate licenses for the feature. You cannot configure or use a feature if the correct license for that feature is not present in the license file. Enable and use the high availability feature only when the license file contains an HA license called Feed High Availability Config 1. In this screenshot, notice there are 2 ASBCE HA devices installed. This concludes the high availability module. You should now be able to describe the hardware configuration for an ASBCE high availability solution. Summarize how the primary and secondary ASBCEs operate during a failover. State the purpose of each subnet that is often used in an HA deployment, and explain why the GARP protocol is critical during an ASBCE failover. Are you able to complete everything listed here? This module focuses on configuring the IP office to implement the ASBCE. Configuration changes to IP office are required to adopt SIP trunking as the primary connection to the PSTN or public switched telephone network, and to include the ASBCE in the network. Let's review the objectives so that you know what this module covers. By the end of this module, you should be able to verify the VoIP protocols are enabled, add SIP users and extensions, configure the IP office components listed on the slide to use the ASBCE, and troubleshoot the SIP trunk configuration using SSA or System Status Application and Sysmon or System Monitor. The first step in integrating the ASBCE with IP Office is to set up the SIP users and extensions so that they can use the SIP phones on the network. This step includes verifying the protocols are in place and adding SIP users and extensions. Next, we complete additional configuration on IP Office to enable the SIP lines and the ASBCE. Finally, we troubleshoot the SIP line to ensure we are able to make and receive calls, and the SSA and Sysmon tools indicate everything works correctly. There are two tools that can be used to configure Avaya IP Office. The Avaya IP Office Manager is a thick client installed on your desktop. Configuration completed in the IP Office Manager thick client is done offline and then applied to the IP Office with a save or update. The second tool is Avaya IP Office Web Manager, which is a browser-based tool accessed through a URL. Web Manager updates are done directly online, therefore, the changes are made and applied more quickly. Both tools enable you to configure IP Office, but the look and feel of the two applications is very different. For this training, we'll use the Web Manager. Let's take a look at how Web Manager works in configuring IP Office. Now let's discuss the first few steps in the process, which are to verify that the protocols are correct and enter SIP extensions and users. You may use the Avaya IP Office Manager or the IP Office Web Manager for this configuration. We'll use the Web Manager. First, log in to the management tool with your username and password. Before adding users and extensions, confirm that VoIP protocols are enabled and the domain is specified. Hover over System Settings at the top of the screen. Click System in the drop-down menu. Select the Avaya IP Office you are configuring with the button on the right. The IP Office has two network interfaces. Enable SIP only on the interfaces that you plan to use. In this example, we will use LAN 1. Therefore, select LAN 1 in the left navigation pane and then select the VoIP tab at the top of the screen. Use this screen to determine which protocols are supported by IP Office. Verify that H.323 Gatekeeper Enable shows yes to support phones requiring the H.323 protocol. Leave Auto Create Extension as a no because this setting is sometimes used for H.323 phones and not SIP extensions. In addition, auto creation for H.323 and SIP should be avoided due to security concerns. Verify that SIP Registrar Enable has a yes to support SIP phone registration. Populate the SIP domain name field with ITSP domain. The SIP domain field must be filled in if SIP resiliency is used. Otherwise, it can be left empty or a meaningful domain name can be used. Please note that this domain is specific to IP Office and is not related to the SIP trunk provider. If TLS is used for SIP signaling, the IP Office root certificate will have to reference this domain in the subject alternate name. Please consult the security documents for more details. If IP Office has an FQDN or fully qualified domain name that is resolvable to the IP Office address in the private network and to the SBC IP address when accessed through the Internet, enter the FQDN. Notice, if changes were needed in this screen, you must change to offline mode. We'll show how to change to offline mode later in this module. No changes were required here, so now we'll create a SIP user with an extension. To enter a SIP user, hover over Call Management and select Users. Then click Add User. Select the desired IP office. Enter the user's name and full name. Enter the password that will be used during application login. Use the application's password to log in as a 1X user. The password is also used for Avaya SIP applications such as Equinox. Re-enter that same information in Confirm Password. Then, enter the extension number based on your dial plan. Select the profile for this user. In this example, we'll select Power User. Notice that once you select Power User, the values in the Applications section change based on the profile's assigned functionality. Note that if you are using Release 11 of the Web Manager, the fields have slightly different names. If necessary, refer to the R11 documentation for additional information. In Login Code, enter the password used for logging into the phone. If you use a login code such as 123456, an error message displays because the security settings require a more complex code. Re-enter that same information in Confirm Login Code. Review the screen and make any additional changes. Then click Create to save the new user. When prompted, select the SIP extension to specify which protocol to use. Notice the blue box indicates you added the user successfully. Remember, it is a best practice to have a PRI line as a backup to the SIP line. Since adding a PR line is not directly related to adding an Avaya SBC to your Avaya IP Office configuration, it is not included in this training. For more information, refer to your IP Office documentation and training. It is necessary to conduct some additional configuration in Avaya IP Office to set up the SIP functionality and integrate the ASBCE. To fully understand this section, it is expected that you already have a solid understanding of IP Office and its basic configuration. This section focuses on the additional settings needed to add the ASBCE successfully. Before completing the configuration to add the ASBCE, 3 tasks should be completed. First, initialize the IP Office and complete its basic configuration. Then, load all the required certificates. Finally, purchase and download the correct number of SIP trunk licenses. Now let's take a look at the configuration of IP Office. The first step to configure IP Office is to confirm you have enough SIP trunk channels licensed and installed. We'll use the IP Office Web Manager for this process. Within IP Office Web Manager, hover over System Settings in the menu bar and select Licenses. To see license information, locate the server that you are configuring, then click the button to its right. Review the license information for SIP trunk channels. If you don't see the correct number of licenses that were purchased, Go to the Web LM and download them. The next step is to establish the server and LAN settings. To select the server and its location, hover over System Settings and then select System in the menu. Locate the IP Office server to configure and click the button to its right. In the Name field, enter a descriptive name for the server. In this example, that step is already finished. If necessary, use the Location drop-down menu to select the correct location that was entered in IP Office during the initial setup. In this example, a location was not established in the configuration. The next step is to configure the network settings to enable SIP trunking. From the System Configuration screen, click LAN 1 to the left. Then click the VoIP tab at the top of the screen. At the top of the screen, notice it says that these settings can only be changed in offline mode. By default, IP Office Web Manager operates in real time and configuration changes are applied to the IP Office system immediately. For some configurations, like adding port information, it is necessary to change the default and go offline. To change to offline mode, click the current user icon and then select Offline Mode. Click OK to acknowledge that offline mode has been enabled and that you will apply changes by clicking Save to IP Office. Now navigate to the System Configuration VoIP screen again. In this screen, verify the SIP trunks Enable field says Yes. Confirm the UDP and TCP fields say Yes and contain the correct port numbers. These fields are for the SIP phones and are not related to the SIP trunks. With the ASBCE, the keep alives need to be enabled for RTP and RTCP. Therefore, select RTP/RTCP in the Scope field. We recommend that periodic keep alives are set to 60 seconds. This setting enables IP Office and ASBCE to open holes in the firewall to be able to receive SRTP. Set the initial keep alives field to Yes. Since changes were made, click Update. Remain in offline mode and click the Network Topology tab to further define elements in the network. In the Firewall NAT type or Network Address Translation type field, there are many options. Select Open Internet in the drop-down menu, since the IP address used is that of the system LAN interface. When this field is set to Open Internet, the STUN protocol will not be used. The value in the Binding Refresh Time field specifies how often the connection to IP Office is refreshed. Enter the number of seconds between each refresh. When the public IP address field is set to the default of 0.0.0.0. IP Office uses the LAN 1 IP address. We'll keep the default. Click Update to save your changes. The changes were made successfully. Now save to IP Office so these offline changes are pushed to IP Office. There are many ways to complete this save, including the Save to IP Office link at the top of the screen. And if you forget as you start to log out, IP Office reminds you. Now return to online mode by logging in again to IP Office Web Manager. In this section, we provision the SIP line and configure the optional DNS server. Hover over System Settings and navigate to Lines. Click the Add Line drop-down and select SIP line. Also, select the server you are configuring. The requirements for provisioning SIP trunking services vary by the service provider. In our example, the options chosen are specific to Avaya Aura Communication Manager, which provides our carrier services. The line number field designates the SIP line for a specific provider. Select any number to use throughout the configuration process. In the ITSP domain name field, enter the domain name used by IP office. The default zeros in national prefix and international prefix fields are wildcards that represent the 1 or 2-digit number dialed when making a national or an international call. Confirm the in-service field says yes to register the SIP trunk and ensure it is available for calls. Verify the Check OOS field says yes so that the system regularly checks if the trunk is in service. This feature ensures the outgoing call routing is not delayed waiting for response on a SIP trunk that is not currently usable. In the Incoming Supervised Refer field, select Always so IP Office will always accept a refer that is sent by the far end. In the Outgoing Supervised Refer field, select Always if IP Office will always attempt to use the refer mechanism to transfer a party to a call leg which IP Office has already initiated. Click Outgoing Blind Refer to display Yes so a user, voicemail system, or IVR can transfer a call by sending a refer to an endpoint that has not set up a second call. Finally, click Create to create the SIP line. Then click OK to acknowledge that the configuration change may result in a momentary disruption in services. Notice the green box displays indicating the SIP line was successfully saved. Click the Edit icon on the SIP line that was just created to access ITSP information. Now click the Transport link on the left. The Transport screen identifies the ITSP or private IP address of the SBC. In this screen, set the ITSP proxy address to the SBC A1 or interior IP address. Set the Layer 4 protocol as TCP. Confirm the Send port field has 5060 to match the port numbers entered in other screens. In the Use Network Topology Info field, select None since there is no net transversal. The next step is optional, depending on whether you are using a DNS or domain name server. If you have a DNS private server, enter the IP address of the server. If a backup server is required, enter that IP address in the next field. If you do not have a DNS server available in your network but want to use one of the many free DNS servers available. For example, the Google DNS's IP address is 8.8.8.8. For our example, this extra step is not necessary. Click Update to save your changes. Then click OK to acknowledge there will be a temporary disruption of telephony services. To add SIP URI or SIP Uniform Resource Identifier information, click the Edit icon for the SIP line created earlier. Next, click the SIP URI or link in the left navigation. Use this link to add SIP URI handling rules for each ITSP account. Click Add to create a SIP URI. The Add SIP channel screen establishes information elements used in the SIP URI. If the call originates from an IP Office endpoint, the settings in the Add SIP channel screen determine whether the settings should be taken from the trunk's SIP credentials or from the user configuration. Since these credentials or settings are often different, the system must be configured to connect, disconnect, etc. correctly. There are a few options for the local URI field. In our example, we'll select Use Internal Data. Then, the user's SIP name is used for the user part of the identity, and the ITSP domain is used for the host portion. For our example, local URI, contact, display name, and the identity fields all display Use Internal Data. In the Send Caller ID drop-down menu, select Diversion Header so that the caller ID uses information from that header. In the diversion header field, change the option to Auto to use the caller information available on IP Office. In the registration field, select from a list of the account credentials configured on the line's SIP Credentials tab. In our example, the default entry is best. Then, enter the line group number in the incoming and outgoing group fields with the drop-down menu or by entering the number in the field. In this example, we'll leave the maximum calls per channel at 10. Then click Create. Now choose the VoIP link and specify how the VoIP calls are managed in the SIP trunk. The codecs selected determine if and how the voice packets will be compressed. In the codec selection field, select either the system default or create a custom entry. Most often, system default is used so that all the codecs are selected to use less bandwidth. In the boxes at the bottom, check whether to support re-invite with the re-invite supported field. Re-invite can be used during a session to change the characteristics of the session. For example, it can be used when the target of an incoming call or a transfer does not support the codec originally negotiated on the trunk. In our example, we'll keep the default. To save your changes or exit this screen, click Update. Then click OK to acknowledge the momentary disruption. Once the SIP line is created, incoming SIP calls are routed using incoming call routes. Next, add a new call route for these calls. In the System Settings drop-down menu, select Incoming Call Routes. Then click Add Incoming Call Route and select the server. In Line Group ID, enter the line number you've been using. In the Incoming Number field, enter the country code, area code, and SIP trunk number from your dial plan. The 4 X's represent the 4-digit extension. In this example, when an incoming call is placed, IP Office matches the first 8 digits of the phone number in the incoming number field to route the call. Therefore, a call made to 476-936-023-602 matches the first 8 digits. The last 4 digits dialed, or 36102, determine the destination or the 4-digit extension of the person who needs to be reached. In the Destinations section, configure the extension options. Click Add to add a destination. In the Time Profile field, select the desired value. Since the destination can be a combination of many digits, enter the hashtag in the Destination field. The hashtag indicates that any 4-digit combination in the extension can be used to route the call. Finally, click Create to save the new destination. Click Create again to save the new incoming call route. The call route was entered successfully. The next step is to provision the user's SIP configuration so the user can place SIP calls. Since these plans are associated with users, click Call Management and Users. Click the Edit icon next to the user you want to configure. Since this user has already been configured, click the SIP link on the left to complete the user's SIP configuration. Format the user's SIP name using the information in your dial plan. In this example, we'll enter the 2-digit country code, area code, and SIP trunk number, and the user's extension number. Enter this same information in the contact field. We'll use the extension information for the SIP display name. Click Update to save your changes. Once the first user is updated correctly, repeat these steps for all SIP users. The next step is to provision the shortcodes. IP Office requires a shortcode to match the number dialed to an action. The number dialed or part of the number dialed can be used as a parameter for the feature or action. To provision the shortcode, click System Settings and select Shortcodes. To add a new code, click the button in the upper right corner. To search for an existing code, use the search field. There are two codes that meet the search criteria since this same code is needed for the primary and secondary IP office. In the code field, 9N was entered to indicate IP office collects and sends any digits followed by 9 to the SIP or PRI trunk. In the feature field, dial was the correct option because that action occurs when the shortcode is triggered. In the telephone number field, the letter N, quotation marks, the @ symbol, and the A1 or private IP address of the Avaya SBC, and then another quotation mark was entered. This entry routes a number followed by 9 to the A1 IP address of the Avaya SBC. The line group ID field indicates the digits dialed will be handled by the SIP line and trunk. Changes are not needed for these shortcodes, so let's discuss an optional step. We'll start with creating ARS shortcodes to match the number dialed to an action. In the System Settings menu, select Alternate Route Selection. Now, click the Edit icon for the main ARS in the primary IP office. Now, add a shortcode for the ARS using the Add functionality. In the Add Shortcode screen, enter a value in the code field. In this example, we'll use a question mark. In your system, select a code based on the dialing rules and other codes configured earlier. In the feature field, select the action or feature that occurs when the shortcode is triggered. In this example, leave dial as the value. Enter a period in the telephone field to dial the full set of dialed digits that triggered the shortcode match. The line group is 17 to match the outgoing group ID in SIP URI. It is not necessary to force account code or force authentication code, so change these values to no. Then click Create. A message displays indicating the shortcode for the ARS was added successfully. This concludes the basic ARS settings. You have now finished the configuration of the Avaya IP office so that the Avaya SBC can be integrated. If the Avaya SBC will be used for remote users, configure the IP office for the remote user as well. If the Avaya SBC is not used for remote users, do not complete these additional steps. First, verify that IP office has sufficient power user licenses. Click System Settings and select Licenses from the menu. To select the IP office, click the button to the right. Verify that the desired number of power user licenses display. Once the licenses have been checked, confirm the user has been given permission for the desired endpoints. To access the list of users, click Call Management and then select Users in the drop-down menu. Click the Edit icon across from the user requiring remote user functionality. In the Profile field, confirm that Power User was selected for applications like Equinox are used. In the Applications section, confirm the correct values are selected. If the user needs access to Avaya 1X portal, confirm Enable 1X portal services displays as Yes. Enable Avaya Communicator as well. Mobile VoIP client is used for 1X VoIP mobility and Equinox on Android and iOS and Equinox. Now click Update to save the configuration. These steps complete the configuration of IP Office to enable remote users. In this training, presents the Avaya ASBCE configuration for remote workers. There are two helpful tools to help with monitoring and troubleshooting. The first tool is SSA, or System Status Application, which is installed with the IP Office Administration Suite. It is a diagnostic tool that is capable of monitoring and reporting the status of the system. It can show the real-time status of activities, such as IP phone registration, trunk channel status, and alarms. System status can also show an inventory of system resources. Access to system status can be controlled through security settings in IP Office Manager. By default, the administrator has access to this application. The additional tool is System Monitor, or Sysmon, which is a trace utility to assist support personnel in diagnosing system problems. The information supplied by System Monitor can be extremely detailed and cryptic. It is good to be able to capture information even if you don't have the background to interpret all information it provides. Filters can be applied to limit the activity reported, and color coding can highlight a specific protocol or event in order to isolate the problem and narrow the focus of their investigation. We'll start with the System Status Application, or SSA, as our first diagnostic tool. SSA provides many useful tools that are explained in more detail in other Avaya IP Office training classes and documents. We'll focus on the functionality used to make some SIP calls and analyze the output from the system. In this example, there is a system status icon on the desktop. Another option is to go to the Windows Start icon and find IP Office in your list of programs. Within the IP Office folder, click System Status to open SSA. In the logon screen, enter the IP address of your IP Office. Then, enter a username and password. In this example, the username is administrator and the password is admin123! Then click Log On. When you first log on to SSA, the System Hardware Summary screen displays, detailing information about the system modules. The format and layout of the screen will vary according to the type of IP Office control unit. Click Trunks in the left navigation pane to analyze IP Office trunks and connections, including VoIP, analog, and digital connections and their current statuses. Click the SIP line in the table. Click Select at the bottom of screen to display the line's trunk data. The IP Office System Status screen displays. Notice the default is the Status tab. Click Trace All to start a trace. The trace displays for all calls associated with the trunk or extension. To verify the system is configured correctly, place a call on an external extension via a SIP trunk. In our example, we'll use Avaya Communicator and Avaya 1X Communicator to place the calls. Enter the correct extension to place the call. After some time, answer it. After more time, end the call. Analyze the output from the call to ensure the system works correctly. If desired, make some additional calls between different phones to see different trace information. Review all of the steps by the SIP protocol, such as inviting to a call, trying to connect, and connecting a call to ensure all steps work. Evaluate this information to see if you locate any errors or problems. Now, we'll move to learn more about System Monitor. This tool also has a great deal of functionality, so we'll only focus on directing Sysmon to the correct IP Office instance, creating a few filters, and viewing key information in the trace. In our example, there is a monitor icon on the desktop. Another option is to go to the Windows Start icon and find IP Office in your list of programs. Within the IP Office folder, click Monitor. The first time after installation, Monitor starts with the default IP address settings. Monitor stores the last good connection and tries to connect with the last IP address. To change the IP Office IP address, click File in the menu bar, then select Select Unit. change the IP address to connect to your IP office. Select UDP as the protocol. Enter the password if needed. Changes are not needed, so click OK. As soon as monitor connects, it displays system information. Let's change the filters to ensure the SIP information displays. Either use the Filters option in the menu bar and select Trace Options, or click the Filters button in the toolbar. For this demo, use Clear All in the All Settings screen to delete the existing filters. When you leave Sysmon running or need assistance from a support team, always ensure Sysmon is using the default options. Then click Yes to confirm you want to clear all trace settings. Click the SIP tab. Click all the desired SIP options. To highlight the different packets with different colors, right-click on the options you just checked. Select the color that will be used to show that packet. Dark and bright colors work best. Then click OK in the color screen. Notice the front of the packet you selected displays in the new color. Repeat this process for any additional packets if desired. Now click the System tab. Select the Print option so that all the trace options are activated. Also, check the prefix HH:MM:SS to convert the timestamp into the hour, minutes, and seconds format. Then click OK to save the changes made on both tabs. Before making a SIP call, clear the display with the X button. Or click Edit and select Clear Display in the drop-down menu. To confirm the system is configured correctly, make a call using a SIP phone. In our example, we'll use a Avaya communicator and a Avaya 1X communicator to make the call by entering the correct extension. After some time passes, answer the call. After more time, end the call. To see the screen better, minimize your telephones. Once these events are complete, click Pause in the toolbar. Or click View in the menu bar and select Freeze Screen Logging. Analyze the events of the call. For example, find the invite message. Notice different messages display in the colors you specified earlier. Scroll down to find the ring message. Finally, locate the bye message when the call ended. Continue your analysis of these messages to determine if you have any issues that need to be addressed. Notice the System Monitor is a more powerful tool than the SSA. It allows you to view part of the call to complete your troubleshooting rather than the entire call displayed in SSA. This slide concludes this module in which you learned how to configure the IP office to implement the ASBCE. Review the objectives displayed here to remind yourself what you learned. If needed, go back and repeat sections that you need to review. In this module, we will upgrade the Avaya ASBCE from version 7.2 to 8.0. At the end of this module, you should be able to list some of the prerequisites that must be completed before an upgrade, upload the upgrade and ASC files to the EMS Element Management System, verify the integrity of the files using the MD5XUM command, install the upgrade and ASC files to upgrade the Avaya SBCs, verify the upgrade of the ASBCE using CLI, and understand when migration may be required and how to migrate an existing configuration. Before attempting an upgrade to the Avaya SBCE, complete the following steps to ensure the upgrade goes smoothly. First, it is always a good practice to create snapshots or backups before performing any upgrades. Snapshots of the EMSs and ASBCEs can be taken using the Graphic User Interface, GUI, or the Command Line Interface, CLI. Save the snapshot or backup file on an external storage device. In case there is a need to revert the VMware snapshot, the EMS should be restored first, and then the ASBCEs. The current Avaya SBCE has to be at least at version 7.2.2 or above before it can be upgraded to version 8.0. Please refer to the latest release notes for the upgrade paths available. Inspect the hardware of the Avaya SBC to ensure that there is no damage. Test the power cycle to ensure the servers passes the post or power on self-tests. Verify that there is sufficient disk space available for the upgrade and that there are no alarms related to disk space. Remember to disable all debug logs. Lastly, download all the files for the upgrades, patches, and fixes using the PLDS website. Before updating the ASBCE, it is always recommended to read the release notes for the version of the software that you will be upgrading to. For example, if upgrading to version 8.0, use the release notes for version 8.0. For the actual upgrade procedures, please refer to the latest version of the document Upgrading Avaya Session Border Controller for Enterprise Release 8.0 document. Here, we can find all the steps for the upgrade process. Please follow the steps indicated in the document for the upgrade process for the various type of devices and configurations. With the release of version 8.0 to prevent issues with the upgrade process, a pre-upgrade utility is now available. This can be used to verify that the particular release of the image can be upgraded to release 8.0. In case the pre-upgrade check fails, it is recommended to use the migration process to migrate to release 8.0. If you are upgrading from 7.2.2 to 8.0, there are two different types of files that are required. These files are called the upgrade and the ASC files. For example, we are upgrading to version 8.0.0-19-16991. The version of the file is indicated in the file name. Use the MD5 sum numbers on this screen to verify that the entire file is downloaded correctly. You'll learn more about this process in a few minutes. Please note that the recommended method of uploading the files to the EMS or Avaya SBCE is using a SFTP client application such as WinSCP. This client application avoids any errors that might be caused during a file transfer. Upgrading the Avaya SBCE from 7.2.2 to 8.0. To begin the upgrade, open the ASBCE EMS in a browser using HTTPS and its IP address. Log in to the EMS using UCSec username and password. Before upgrading the ASBCE, we need to verify some information. From the ASBCE dashboard, navigate to System Management. The Devices tab appears in the right-hand side window. The active devices appear in the window and display the device names, management IP addresses, the versions of the devices, and the status of each of the servers. Before performing any upgrades, it is important that all the servers are in the commissioned state. If the Avaya ASBCE servers are configured as a high availability pair, ensure that HA state is primary and secondary, respectively, as seen in the example we're going to use for this video. Also, verify that the version of the Avaya ASBCE is at least 7.2.2. Log out of the ASBCE dashboard. We will return to the dashboard once we have uploaded the upgrade and the ASC files. To upload the files to the EMS server, we can use a SFTP client application such as WinSCP. Start the WinSCP application. At the top of the WinSCP screen, the SFTP protocol is selected by default. Enter the IP address of the EMS and port number 222. Next, enter IPCS, username, and password. Finally, click Login. Once logged in to the EMS, navigate to the location of the required file on the local server in the left-hand window pane. Upload the upgrade and ASC files from the local server to the home IPCS directory on the EMS. This directory is the default location of the files on the EMS. Select the files and then click Upload and OK. Uploading the files may take time depending on the speed of your connection. Once the files are uploaded to the EMS, exit out the WinSCP application. After the files have been uploaded to the EMS home IPCS directory, they need to be moved to the Archive UR Packages directory. To do that, we can use an application such as PuTTY. Log in to the EMS. Use port 222 and select the correct session from the saved sessions list. Click Load and then Open. Log into the EMS as the IPCS user. To move the files, root privileges are required. Log in using the SU command and password. Verify that the upgrade file exists in the home IPCS directory using the ls command. Once you confirm the files are in this directory, copy these files to the Archive UR Packages directory. Move the upgrade and ASC files using the move command, mv, the file name, and the destination directory name. Repeat this same process for the ASC file. Change to the directory to the upgrades. To verify the integrity of the upgrade file, use the md5sum and the file name. Verify that the MD5 checksum generated by the command matches the checksum value shown in the original file name. Exit out of the PuTTY application. Return to the EMS dashboard. Click System Management. Then, click the Updates tab in the right-hand side window. Notice in the Upgrade from Local File field, the upgrade package available is displayed. Click on the Upgrade button to start the upgrade process. Once you click the Upgrade button, the EMS sends a message confirming that you want to start the upgrade. The message displays the current version and the package version, so you can verify the version to which the EMS is going to be upgraded. Click on Start Upgrade to continue with the installation process of upgrading the EMS first. Once it begins, an upgrade status screen appears with the message, "Please wait. Your EMS upgrade is currently in process." This process may take a long time. Once completed, a message displays indicating the process was completed. Also, that to upgrade your devices, please log in and navigate back to the upgrade screen. click Return to EMS to navigate to the login screen. As you did previously, log into the EMS and navigate to Device Management tab. The EMS indicates it is on version 8.0 and in the commissioned state. Also, that the ASBCEs require an upgrade. Click on the Updates tab in the right-hand side window. The message displays that one or more devices are in an orphan state. If you would like to upgrade these devices now, please click on the Upgrade button below. Click on Upgrade. From the Upgrade Devices window, click on the Device Name checkbox. This will select the first ASBCE to be upgraded. The system selects the primary ASBCE to upgrade first. Click on Next. The system starts the upgrade of the first ASBCE. Once the upgrade is completed, the upgrade status indicates the status as completed. Click on Finish. Since our environment contains a high availability pair, a message displays that one or more devices are in an orphan state. If you would like to upgrade these devices now, please click on the Upgrade button below. Click on Upgrade. Next, click the checkbox in front of the device name. The system now selects the second Avaya SBCE for upgrade. Click on Next. Once the upgrade is complete, click Finish. After the completion of the second Avaya SBCE upgrade, the Upgrade tab indicates that there are no upgrades available. In the Devices tab, notice the primary and the secondary Avaya SBCE have been upgraded to version 8.0 and that all the devices are in the commissioned state. This completes the upgrade process using the EMS graphic user interface. We can also verify the version of the upgrade using the CLI. Log into the EMS using the PuTTY application and run the command IPS-version. The SBCE and application version should be 8.0.0.19-16991. When the pre-upgrade check fails, the migration of the current configuration to release 8.0 may be required. Use the following procedure to migrate an ASBCE currently in release 7.2.2 or 7.2.2.1. Create a backup of the current server and download it to an external local device. Install a new version 8.0 primary EMS or ASBCE with the same management IP address. The new server can be installed on the same location where the backup file is saved. For details, refer to the Deploying ASBCE documentation. Copy the .tar backup file to the upgrade directory on the EMS or ASBCE. Run the Restore Backup command to restore the backup data. Refer to the ASBCE upgrade documentation for details. If there exists a primary and secondary EMS, then the secondary also has to be migrated for the changes to take effect on the secondary EMS. Restart the migrated EMSs and then the associated ASBCEs. You should now know how to upgrade the Avaya SBC from 7.2.2 to 8.0 and have seen the videos to help you with that process. You should now be able to list some of the prerequisites that must be completed before an upgrade, upload the upgrade and ASC files to the EMS, Element Management System, verify the integrity of the files using the MD5sum command, install the upgrade and ASC files to upgrade the Avaya SBCs, and verify the upgrade of the ASBCE using CLI. In this module, we will look at all the steps that need to be followed to configure a SIP trunk on the SBC. By the end of this module, you should be able to list the prerequisite conditions necessary to configure SIP trunking, perform the pre-installation procedures, Perform the SIP trunking configuration using TCP, using the configuration steps as follows. Reviewing preliminary checklist. Configuring topology hiding profiles, the interworking profiles, call server profiles, routing profiles. Configuring the signaling interfaces and media interfaces, the domain policies, the endpoint policy group. And finally, server flows, where we will combine all the profiles and rules together to create the call server and trunk server flows. Secure SIP trunking saves SIP trunk-enabled enterprises to completely secure SIP connectivity over the Internet, thus ensuring the privacy of all calls originating within the enterprise network or from an external network without the need of a VPN. Because the SBC security device is deployed in the enterprise DMZ as a trusted host, all SIP signaling traffic destined for the enterprise is received by the external firewall and sent to the SBC device for processing. This secures the communication between the call servers and trunk servers. The SBC also helps in performing protocol repair when the implementations of SIP has variations, allowing the SBC to adapt to the requirements of the Internet telephony service providers. One of the key benefits of the SBC is that if the signaling traffic is encrypted, it device decrypts all TLS encrypted traffic and looks for anomalous behavior before forwarding the packets through the internal firewall to the appropriate IP PBX in the enterprise core to establish the requested call session. Here is a generic checklist for configuring the Avaya ASBCE SIP trunk with the IPO as the call server and a trunk server, which can be a public ITSP, Internet Telephony Service Provider, or in our example, an Avaya Communication Manager. The steps required to configure the SIP trunk are as follows. Starting off with reviewing the preliminary checklist, the configuration is done in groups of features. The first group is the profiles, where topology hiding, interworking, and routing profiles are configured. The next step is creating the signaling and media interfaces. Go on to the server configuration for call and trunk servers. The domain policy administration consists of creating the application, security, signaling, and media rules. The endpoint policy group will tie in all the rules together. Next, the server endpoint flow will combine all the profiles and rules together. Finally, after all the above configurations have been completed, test calls can be made between the call server and the trunk server. In this video, we will configure a SIP trunk for the SBC. Prior to starting the SIP trunk configuration, the SBC must be in the commissioned state. Let's log in and look at the configuration of the SBC. From the dashboard, navigate to System Management, and under the Devices tab, you will find the state of the servers. Verify that the status of the servers is in the commissioned state. Next, verify that the private and public interfaces of the SBC have IP addresses assigned to them. From the device-specific settings, select Network Management, and then, on the right-hand pane, Networks. Verify that the A1 and B1 interfaces are configured with IP addresses. The interfaces also have to be verified to be in the enabled state. From the Interfaces tab, see the A1 and B1 ports are in the enabled state. The first step in the configuration of the SIP trunk, either using TCP or TLS, is topology hiding profile for call server and trunk server. To create the topology hiding call server profile, start start from the dashboard, select System Management, then Global Profiles. Finally, click Topology Hiding. Click the default and then Clone. Use the default settings as a starting point. Do not change the default settings. Type a descriptive name for the call server profile in the Clone Name field. For example, Call Server TH. Then click Finish. Next, to modify the Call Server TH profile, click Edit to edit the profile. In the Edit Profile Hiding Profile screen, the Replace Action fields for To, From, and Request line have to be changed from Auto to Overwrite. In the Overwrite Value field, enter the domain name for the private network, sip.msol8.com. Repeat these steps for the From and Request line fields. What we are configuring here is the values that the original headers will be replaced by this domain name of the private network for each of these headers, To, From, and Request line. Note, for the headers Via and Record Route, the replace action is Auto. The criteria field for all the headers is IP/domain. Click Finish after filling in the override values. The same procedure is again used to create the trunk server topology hiding profile. From the topology hiding profile screen, click Default and then Clone. Type a descriptive name for the trunk server profile in the Clone Name field. For example, Trunk Server TH. Click Finish to complete the configuration. No changes are required for the SIP headers or addresses since they are coming from the trunk server or the service provider. Verify that both the call server as well as the trunk server profiles appear in the Topology Hiding Profiles tab. This completes the call server and trunk server topology hiding profile configuration. In this video, we will configure the server interworking profile after completing the topology hiding profile. Next, we will configure the server interworking profile. The server interworking profiles allows one to configure some of the interworking parameters of the Avaya ASBCE to function in a voice-over IP network using different implementations of the SIP protocol. To create a server interworking profile for the call server, navigate from the dashboard under Global Profiles and click Server Interworking. For this SIP trunk configuration, both the call server and trunk server interworking profiles are clones of Avaya RU profile. Select the Avaya RU profile and click Clone. Type a descriptive name for the call server profile in the Clone Name field. For example, Call Server IW. Click Finish to complete the configuration. To edit the cloned profile, scroll down to the bottom of the window and click Edit. To configure the settings of the call server, select the T.38 to support fax relay and then click Finish to complete. Next, we will configure Fast Timeout, which has to be enabled for fast response timeout. This is not a mandatory configuration. To change the timers, click the Timers tab and click Edit. Change the Trans Expire timer to 4 seconds to support the fast response timeout. This setting allows changing the timers set by the SIP protocol RFC, which by default is 32 seconds. Click Finish to complete the timer setting. Setting the trans timer to 4 seconds tells the SBC that if the call server does not respond within the set time, the SIP connection is not established. The trunk server uses the exact same setting as the call server IW profile. The trunk server interworking profile can just be a clone of the call server IW profile. Click Clone to make a copy of the call server IW profile. Enter a new and descriptive name, for example, trunk server IW. Then click Finish. This completes the configuration of the interworking profile for the call server and trunk server. The server configuration also requires the call server and trunk server profiles to be created. After completing the server interworking profile configuration, we will proceed to configure the server profiles for the call server and trunk server. To configure the call server profile, under Global Profiles, click Server Configuration. Click on Add to create a new call server profile. Then give the profile a name, call server for example, then click Next. Select the server type as call server. In the SIP domain field, enter the domain of the private network where this SBC is located. The SIP domain configuration is optional. Set the TLS client profile to None. At this time, we are only configuring TCP for the transport protocol. In the IP address FQDN field, type the call server IP address, which in our example is the IP address of the IP office. Set the port field to 5060 and the transport field to TCP. The different options available for transport are TCP, UDP, or TLS. The TLS parameters are not administered here at the present time. TLS requires both CA certificate as well as the identity certificates to be created with the TLS client and server profiles. Click Next. Skip the Add Server Configuration Profile Authentication configuration by clicking Next. Select the Enable Heartbeat checkbox and set the frequency to 30 seconds. For the From URI or Uniform Resource Identifier field, enter the domain address of the source of the SIP options, which in our case is the SBC. It is the resource from where a call originates. For the To URI, enter the domain address of the IP office, which is the resource of the destination where the calls are sent to. This may be useful when debugging Wireshark traces. For the From and To URIs, IP addresses of the servers can also be used instead of the FQDN name. Then click Next. In the Add Server Configuration Profile ping screen, click Next. In the Advanced Configuration window, click Enable Grooming. Grooming enabled allows the system to reuse the same connections for the same subscriber or port. Set the Interworking Profile field to the Call Server Interworking or IW. Click Finish to complete the configuration. Select Add to create a new trunk server profile. Give it a name such as Trunk Server, then click Next. Select the server type as trunk server, which is selected by default. In the SIP domain field, enter the domain name of the trunk server. TLS client profile is set to None. At this time, we are only configuring TCP for the transport protocol. In the IP address FQDN field, type in the IP address of the trunk server, which in our example is the communication manager. Set the port field to 5060 and the transport field to TCP. Click Next. Skip the server authentication and proceed to the next window. Select the Enable Heartbeat checkbox and set the frequency to 30 seconds. For the From URI, enter the domain address of the source of the SIP options, which in our case is the SBC. It is the resource from where calls originate. For the To URI, enter the domain address of the destination of the SIP options, which in our example is the service provider. This is the resource of the destination where the calls are going to be sent to. This information may be useful when debugging Wireshark traces. Then click Next. In the Add Server Configuration Profile ping, click Next. In the Advanced Configuration window, select Enable Grooming. With grooming enabled, it allows the system to reuse the same connections for the same subscriber or port. Set the Interworking Profile field as the Trunk Server Interworking IW profile. Click Finish. This completes the configuration of the server profile for the call server and trunk server. Routing profiles identify a particular call flow and thereby ascertain which security features are applied to these packets. After completing the server configuration for the call server and trunk server, we will next configure the routing profiles. The routing call server profile for inbound traffic is the traffic sent from the ITSP trunk server to the call server. In our example, traffic is sent from the communication manager to the IP office server. To create the call server routing profile, starting from the SBC dashboard under Global Profiles, select Routing. Click Add to add a new routing profile for the call server. Give the call server routing profile a name. Call server TCP, for example. We use TCP for the routing profile name to indicate that this routing profile is for TCP transport. It is different from the routing profile we create for the profile for the TLS transport. Now click Next. In the routing profile screen, the Next Hop Priority checkbox is selected by default. Click Add to add a Next Hop address. This means that when a packet is received by the call server routing profile, the packet is sent to the next hop, which is the IP address of the call server, which in our example is the IP address of the IP office. Fill in the priority weight of 1. For the server configuration, select the call server from the drop-down menu. The IP address of the call server, along with Transport Protocol TCP, automatically displays in the next hop address field. The priority of 1 indicates that the packets will have the higher priority over any other packets in the network. Click Finish to complete the call server routing profile. The routing trunk server profile for outbound traffic is the traffic sent from the internal call server to the ITSP trunk server. In our example, it is the traffic that is sent from the IP office server to the communication manager. Click Add again to add a new routing profile. Give the trunk server routing profile a name. Trunk server TCP, for example, and click Next. Again, the Next Hop Priority checkbox is selected by default. Click Add to add a Next Hop address. This means that when a packet is received by the trunk server routing profile, the packet is sent to the next hop, which is the IP address of the trunk server, which in our example is the IP address of the communication manager. Fill in the priority weight of 1. For the server configuration, select the trunk server from the drop-down menu. The IP address of the trunk server, along with Transport Protocol TCP, automatically displays in the next hop address. The priority of 1 indicates that the packets will have the higher priority over any other packets in the network. This completes the configuration of the routing profile for the call server and the trunk server. The routing call server profile for inbound traffic, that is, traffic sent from the ITSP trunk server to the call server. This uses the call server routing profile. The routing trunk server profile for outbound traffic, that is, traffic sent from the internal call server to the ITSP trunk server. This uses the trunk server routing profile. For managing the device-specific settings, two device-specific features have to be defined: the signaling interface and the media interface. Media interfaces, external and internal. The signaling interface will be configured first. This is required for managing the device-specific settings. Create the external signaling interface, which is the signal sent towards the external trunk server. From the dashboard, under Device-Specific Settings, select Signaling Interface. Click Add to create a new interface. In the Signaling Interface name field, type a name like SIG-EXT, for example. In the IP address drop-down list, select Network's public B1 VLAN 0, which is the public interface of the Avaya SBC. The IP address is placed automatically. Assign the port numbers for the protocols that were assigned to the server profile. For the TCP and UDP ports, 5060 is already selected. Leave the TLS port blank because we are using TCP for the transport protocol. Check Enable Shared Control when dual registration of two separate devices is required for the same user. The port used for this is 5063. Click Finish to complete the external signaling interface configuration. Click Add to create a new internal signaling interface, which is the signal sent towards the call server. In the name field, type a name like SIG-INT, for example. In the IP address field drop-down list, select Network's private A1 VLAN 0, which is the private interface of the Avaya SBC. The IP address is placed automatically. The TCP and UDP ports already have been assigned the port 5060. Click Finish to complete the internal signaling interface. We will next configure the media interfaces. Here, we define the ports and the interfaces that the SBC uses to transport the media traffic, which are the voice and data packets that are sent to the servers and endpoints. From the SBC dashboard, under the Device-Specific Settings, select Media Interface. Click Add to create a new media interface. In Media Interface Name field, type a name, MEDEXT, for example. In the IP address field drop-down list, select Network's public B1 VLAN 0, which is the public interface of the Avaya SBC. Once again, the IP address is placed automatically. The port range of 35,000 to 40,000 is already selected by the system. Just like the signaling interface, the media interface uses TCP for transport, so no TLS is configured. Click Finish. Click Add to create the new Media Internal Interface. In Media Interface Name field, type a name, MEDINT, for example. In the IP address field drop-down list, select Network's private A1 VLAN 0. It is the private interface of the Avaya SBC. The IP address is placed automatically. The port range of 35,000 to 40,000 was already selected by the system. Click Finish. This completes the configuration of the signaling and media interfaces. Domain Policy Administration. SIP trunking uses these 5 Domain Policy Administration rules to control the call flows entering or leaving the enterprise network. Call and trunk server rules and a policy group have to be applied using each of the 5 elements: application rules, media rules, security rules, signaling rules, and an endpoint policy group that ties together all these rules. Application rules will be configured first. It is used to size the number of audio or video sessions processed by the Avaya SBC and also determine whether the traffic is either incoming or outgoing. To create a domain policy application rule for call server, click Application Rules under Domain Policies. Click Default in the Applications Rules list and then click Clone. Give the application rule for call servers a descriptive name in the Clone Name field. For example, enter Call Server AR, then click Finish. For call server application rules, the default setting includes the maximum number of 200 concurrent audio sessions, with a maximum number of 5 sessions per endpoint. This rule can be edited for the number of concurrent sessions, for audio, video support, CDR call detail record support, and to enable RTCP, Real-Time Control Protocol, keep alive if required. Click Edit to set the call server application rules parameters. Change the maximum concurrent sessions and maximum sessions per endpoint to 500. These fields are over-provisioned because some sessions take a while to clear. Modify the other parameters as necessary. Click Finish to save the changes. Configure the application rule for trunk server next. Click Call Server AR and then click Clone. In this example, use the same application rules that were set for the call server. Give the application rule for trunk server a descriptive name in the Clone Name field. For example, Trunk Server AR, then click Finish. Now we'll move to another set of rules. The Domain Policy Administration Media Rules define the media packet parameters, such as encryption techniques and encryption priority for either real-time protocol or RTP or secure real-time protocol or SRTP. To create a domain policy media rule for call server, go to the dashboard. Under Domain Policies, click Media Rules. Click Default Low Med in the Media Rules list and then click Clone to use the default low encryption configuration. The clone configuration has the defaults that have already been set. We'll see more about these defaults shortly. Give the media rule for call server a descriptive name in the Clone Name field, such as Call Server MR, then click Finish. Verify that the newly created call server media rule appears in the Media Rules list. In the Encryption tab, notice the preferred format is RTP as opposed to SRTP. If SRTP encrypted media is required, the default low med ENC rule can be used. Use the default configurations for the QoS quality of service. The QoS for the media packets uses DSCP, Differential Services Code Protocol, by default. For audio and video QoS, the setting is EF, or Expedited Forwarding. This provides higher priority to the voice and video packets compared to the signaling packets, which have the QoS set to AF, Assured Forwarding. In the Advanced tab, additional parameters can be configured. For instance, Silencing Enabled allows for media silencing. If no media packets are detected within the set timeout, the Avaya SBC sends an incident report to the syslog and the call is disconnected. BFCP, or Binary Floor Control Protocol, is used for video conferences. FECC, or Far End Camera Control, and ANAT, or Alternative NAT, are used in mixed IP version 4 and IP version 6 environments and are available for configuration. In our example, no changes are needed. So we'll proceed to preview the Codec Prioritization tab. Enable the codec prioritization by selecting the Codec Prioritization checkbox or checkboxes. This option is useful when the same connection is used for services other than just audio and video media. Since all the parameters for the media rule for the trunk server are going to be the same as the parameters set for the media rule for call server, clone the rule that we just created. Click the call server MR rule in the media rules list, then click Clone. Give the media rule for trunk server a descriptive name like trunk server MR. Then click Finish. Now we finished media rules for the call server. The next sets of rules we will configure are the security rules. With domain policy security rules, the compliance, scrubber, and domain DOS, denial of service, and DDoS, distributed denial of service, parameters are configured. There are 3 default security rules: default low, default MED, and default high. They are chosen according to the network requirements. To create a domain policy security rule for the call server, go to the dashboard. Under Domain Policies, select Security Rules. Click on Default Low in the Security Rules list. The default low contains the basic or standard configurations for security. The other defaults are for medium and high security configurations. Now click Clone. Give the security rule for call server a descriptive name such as call server SecR, then click Finish. Use the Scrubber tab to enable protocol scrubbing that checks incoming SIP signaling messages for various types of protocol-specific events and anomalies. We won't use this configuration. Use the domain DOS to configure the thresholds for the number of SIP messages that are received by the SBC. It is not necessary to complete this configuration for our example. To create a domain policy security rule for trunk server, we'll use the call server's configuration. Click Call Server SecR in the Security Rules list, then click Clone. Give the security rule for call server a descriptive name in the clone name field, such as trunk server SECR. Then click Finish. With signaling rules, the action to be taken for each type of SIP-specific signaling request and response message is defined. Actions include Allow, Block, and Block with Response. To create a domain policy signaling rule for call server, under Domain Policies, select Signaling Rules. Click on Default in the Signaling Rules list and then click Clone. With signaling rules, we define what action has to be taken for each type of SIP-specific signaling request and response. Give the signaling rule for the call server a descriptive name. For example, call server SIGR, then click Finish. In the signaling rules, the other options include how to handle SIP requests, request headers, and response headers that are either coming into or going out of the Avaya SBC. Each of these tabs allows the modification of each of the parameters as necessary. The options include Allow, Remove, or Block with Response. In this tab, the signaling QoS is enabled by default. By default, DSCP is enabled and set to AF, or Assured Forwarding. The UCID, or Universal Call Identifier parameter, when enabled, generates a unique node ID that is assigned to the SBC and can be used across an Avaya solution. This identifier can also be used by other adjuncts for reporting, monitoring, and call recording. We created a domain policy signaling rule for the call server. Now let's clone it for the trunk server. Click on Call Server SIGR in the Signaling Rules list, and then click Clone. Give the new signaling rule for the call server a descriptive name in the clone name field, like Trunk Server SIGR. Then click Finish. This concludes the Domain Policies Administration for Application Rules, Media Rules, Security Rules, and Signaling Rules. Domain Policy Administration. Endpoint Policy Group ties together all the domain policy rules that we created. Server flows define how the traffic is handled by the Avaya ASBCE and applies all of the configuration done earlier. Let's continue with the Domain Policy Administration configuration. After completing the signaling rules, configure the Endpoint Policy Group. This ties together all the domain policy rules that we created for the call or trunk server. From the dashboard, under Domain Policies, select Endpoint Policy Groups. Click Default Low and then Add to create a new policy group. Give the Endpoint Policy Group for Call Server a descriptive name in the Clone Name field. We'll use Call Server Pol Group, then click Next. Set the fields in the policy group to their call server equivalent names for each of the application, media, security, and signaling rules that we created previously. The border rule is left as default. Now click Finish. To create a domain policy endpoint policy group for trunk server, go to the dashboard. Under Domain Policies, select Endpoint Policy Group. Click Default Low and then Add to create a new endpoint policy group. Give the endpoint policy group for trunk server a descriptive name in the group name field, such as Trunk Server Pol Group. Then click Next. Set the fields in the policy group to their trunk server equivalent names for each of the application, media, security, and signaling rules that were created previously. The border rule is left as default. Click Finish. Server flows are also within Domain Policy Administration and define how the traffic is handled by the Avaya ASBCE. Server flows apply to all of the configurations done earlier. From the dashboard, under Device-Specific Settings, click Endpoint Point Flows. Then click the Server Flows tab. Click Add in the right pane to add a new call server flow. Complete the screen according to the example. For the flow name, give the call server a name. For example, use Call Server SIP Trunk Flow. For the server configuration, select Call Server. For the received interface, select Signaling External. For the signaling interface, select Signaling Internal. For the media interface, select Media Internal. For Endpoint Policy Group, select Call Server Pol Group. For the routing profile, select Trunk Server TCP. For the topology hiding profile, select Call Server TH. Leave the URI group, transport, and file transfer profile at their defaults and click Finish. One thing that you need to remember is that the call server flow uses the trunk server routing profile. To create a server flow for trunk server, click Add in the right pane, add a new trunk server flow. Administer the form according to the example. Flow name. Give the trunk server a name. For example, Trunk Server SIP Trunk Flow. For the server configuration, select Trunk Server. For the received interface, select Signaling Internal. For the signaling interface, select Signaling External. For the media interface, select Media External. For Endpoint Policy Group, select Trunk Server Pol Group. For the routing profile, select Call Server TCP. Finally, for the topology hiding profile, select Trunk Server TH. Leave the URI group, transport, and file transfer protocol at their defaults and click Finish. Note, the Trunk Server SIP trunk flow uses the Call Server routing profile. This concludes the configuration of the server flow and the configuration of the SIP trunk using TCP. When a packet is received by the SBC, the content of the packet, such as the IP address and the URI, determines the server flow that the packet matches. The call server flow uses the trunk server routing profile because the trunk server is routing or sending the packet. In the same manner, the trunk server flow uses the call server routing profile. It is the call server which is routing the packet. Please take some time to review this slide, and when you are ready, click the Next button to continue on with this course. The routing trunk server profile for inbound traffic, that is, traffic sent from the ITSP, Internet Telephony Service Provider, to the internal call server via IP office, for example, uses the call server routing profile. Please review this slide to understand the inbound traffic flow, routing profile, and the interfaces used for the inbound traffic. When you are ready, click the Next button to continue on with this course. The routing call server profile for outbound traffic, that is, traffic sent from the private call server via IP office, for example, to the ITSP, uses trunk server routing profile. Please review this slide to understand the outbound traffic flow, routing profile, and the interfaces used for the outbound traffic. When you are ready, click the Next button to continue on with this course. Verification of the SIP trunk using TCP protocol. Both the trunk server and the call server via IP office have to be configured to be able to dial calls as well as route packets between them. Configure the dial plan on the call server. Configure the routing between the call server and the SBC. Test to see a call can connect between the CS and the TS. The screen capture below shows a call between the Equinox client and the external phone number. You should now be able to list the prerequisite conditions necessary to configure SIP trunking, perform the pre-installation procedures, perform the SIP trunking configuration using TCP, using the configuration steps as follows: reviewing preliminary checklist, configuring topology hiding profiles, the interworking profiles, call server profiles, routing profiles, configuring the signaling interfaces and media interfaces, the domain policies, the endpoint policy group, and finally, server flows, where we will combine all the profiles and rules together to create the call server and trunk server flows. This module focuses on configuring the Avaya ASBCE for remote worker using the IP office. After completing this module, you will be able to list the requirement to configure the ASBCE for remote workers, verify advanced sessions licenses are installed, add new IP address for SIP trunk, install certificates and create client and server profiles, create the signaling and media interfaces for internal and external users, Add a new call server profile for remote workers. Create the endpoint policy group. Add a subscriber and server flows. Test the remote worker configuration. The mobile workspace solution focuses on extending the VoIP and UC applications to any supporting endpoint, and this often is used for secure teleworkers, remote users, traveling employees, or even distributed call centers. The solution ensures that all signaling and media can be fully encrypted, all users and devices are authenticated, all access is controlled. Here is a generic checklist for configuring the remote worker to connect to the ASBCE. The steps required for configuring the remote worker are as follows. Verify that advanced sessions licenses are installed. This is required for the remote worker feature. Start off with adding two new IP addresses, one for the internal SIP trunk and the other for the public trunk for remote workers. Then, install the CA certificates for the enterprise users. Use these certificates to create the TLS client and server profiles for the remote workers. The first group is the profiles, where topology hiding, interworking, and routing is configured. The next step is creating the signaling and media interfaces. Go to the server configuration for call and trunk servers. The domain policy administration consists of creating the application, security, signaling, and media rules. The endpoint policy group will tie in all the rules together. Next, the server endpoint flow will combine all the profiles and rules together. Finally, after all the above have been configured, test calls can be made to ensure that the above configurations have been completed successfully. In this video, we will configure the remote worker for the IP office. Remote workers require advanced sessions licenses for this feature. Log in to the EMS GUI interface using the IP address and UCSec username. Remember to use HTTPS. To verify the SBC licensing for the remote worker, navigate to System Management and then the Devices tab in the right-hand side of the pane, which is selected by default. In any one of the SBC or SBC-HA devices, click View to view the system information. Under the Dynamic License Allocation, there should be at least one or more licenses for the advanced sessions. For the remote worker users, new IP addresses for SIP trunks need to be added to the private A1 and public B1 interfaces to separate the traffic between the SBC and remote worker. From Device-Specific Settings, select Network Management, and then click the Networks tab on the right-hand side pane. Click Edit next to the private IP address in the A1 interface. Next, click Add, and then insert the new private IP address for the remote worker internal SIP trunk. Verify that the private IP addresses has been added for the A1 interface. Click Finish. Next, click Edit beside the public IP address in the B1 interface. Then click Add, and then insert the new public IP address for the remote worker external SIP trunk. Verify that the public IP addresses has been added for the B1 interface. Finally, click Finish. As the interfaces were modified, the SBC application must be restarted for the changes to take effect. From the SBC dashboard, select System Management. Then, in the right pane, click the Devices tab, and then click Restart Application. Notice a message is displayed indicating the restart was successful. For the HA configuration, restart both the primary and the secondary SBCs. Return to the device-specific settings and then Network Management. In the Networks tab, verify that the new IP addresses appear in the IP address field. For TLS configurations, SBC Identity Certificate and IP Office Root CA certificates have to be generated and installed. To generate an identity certificate for the SBC, log into the IPO Server Edition using HTTPS, IP address of the IP office, and port 7071 as administrator. Select the Settings tab and scroll down to Identity Certificates. Check the checkbox for Create Certificate for a different machine. In the Machine IP field, enter the external IP address of the SBC. In the Password field, enter a password to encrypt the certificate and the key. Note the password complexity requirements. In the Subject Name field, enter the FQDN of the Avaya SBC. In the Subject Alternative Names field, enter the DNS FQDN of the Avaya SBC. Leave the rest of the fields as default. Click Regenerate. Click the link in the warning pop-up window and save the file to the local desktop. Rename the downloaded file to SBC ID.P12. Then click OK to close the warning window. To obtain the Certificate Authority or CA certificate, click Download PEM Encoded under CA Certificate and save the file to your local desktop. Rename the file as SBC Root CA Cert. Notice the file type must change from .PEM to .CRT. Exit or log out of the IP Office Administration application. The identity certificate generated by the IP Office is a single file that has both the certificate and key files. For the SBC, split this file into two separate files. To copy the identity certificate file, log into the EMS log using the WinSCP application. Use the management IP address of the EMS and port 222 and the username IPCS. Then enter the IPCS password. Select and upload the SBC Identity Certificate SBC ID.P12 file saved earlier to the Home IPCS directory, which is the default directory on the EMS. In the Upload the SBC ID file to Remote Directory window in the right side of the screen, select OK. Then disconnect from WinSCP. We now need to log in to the EMS using CLI to split the CRT file and the key file. Run the PuTTY application to log in to EMS using SSH protocol, the IP address of EMS, and port 222. Log in first using the IPCS username and password, and then as root user. The next command will require a password to be entered for splitting the file, then for the PEM passphrase, and finally for the verification. Use the password that was specified when generating an identity certificate for the SBC. To extract the CRT file first, run the command open SSL pkcs12 minus input filename SBC ID.P12 minus output filename SBC identity cert.crt file. Note that the output filename is now SBC identity cert.crt. Verify the existence of the new file using the ls-l command. To extract the key file, run the command open SSL pkcs12 minus nocerts minus input filename SBC ID.P12 minus output file name SBC identity cert.key file. Note that the output file name is now SBC identity cert.key. Verify the existence of the new file using the ls-l command. To be able to download or copy the files to the local desktop, the attributes of the generated files have to be changed. To change the attributes of the split files, run the following command for both the CRT as well as the key files. Change mode for user, group, and other users of the CRT file to read and execute. Repeat the command using the key file name. Verify that the attributes of these two files have been changed. To copy the identity cert and key files back to the local desktop, log in into the EMS using the WinSCP application. Download the CRT and key files back to the local desktop. Exit out of the WinSCP application. From the local desktop, open SBC Identity Cert file in Notepad. Remove all lines except those which are between the first Begin Certificate and End Certificate lines. Save the new file. Once CRT and the key files are ready, we can begin to upload the identity certificate onto the EMS server. First, log in to the Avaya EMS. From the dashboard, click TLS Management, Certificates, and then Install. Give the name of the certificate as SBC Identity Cert. Choose the CRT and key files and click Upload. Verify that the correct certificate file has been uploaded, and then click Install. Upon successful installation, a message indicating that the installation was successful is displayed. Click Finish. Click Install again to install the CA certificate. Select CA certificate and fill in the name of the certificate. For example, IPO root CA. Select Allow Weak Certificate Key to allow certificates with smaller key size, for example 1024, to be accepted. Choose the CA root file and then click Upload. Click Install to install the CA certificate onto the Avaya SBC. Click Finish to complete the installation. Verify that the identity certificate and the root CA certificates have been installed and appear under the Certificates tab. To continue with the remote worker configuration, this is the second video. We will next create the TLS client and the server profiles. Both require certificates for authentication. When an endpoint tries to contact Avaya ASBCE to set up a TLS connection, the Avaya ASBCE will act as a TLS server. When the Avaya ASBCE tries to contact an internal server, IP office for example, the Avaya ASBCE will act as a TLS client. To create the TLS client profile, from the Avaya ASBCE dashboard, select TLS Management and Client Profiles. Then click Add. Give the client profile a profile name, TLS Client, for example. From the Certificate drop-down menu, select the Avaya ASBCE Identity Certificate, SBC Identity Cert.CRT. This is the certificate that Avaya ASBCE client uses to identify itself. In peer verification, the SBC root CA.CRT automatically displays. It is the certificate authority that the Avaya ASBCE uses for authentication of the remote device or server. Enter the verification depth as 1. The verification depth must be at least 1. It will, however, depend on the number of certificates that exist for the peer device or server. Click Next. To be compatible with other versions of TLS certificates, select all the TLS versions. Select the checkboxes for TLS 1.1 and TLS 1.0 since the system default automatically selects TLS 1.2 only. This is because only the TLS version 1.2 has sufficient level of security. The other versions provide compatibility to older TLS versions. Click Finish. We will next create the TLS server profile. Select Server Profiles and then click Add in the right pane to add a new TLS server profile. Give the server profile a profile name, TLS Server, for example. From the Certificate drop-down menu, select the SBC Identity Cert. This option is usually the case when an endpoint tries to contact the Avaya ASBCE to set up a TLS connection. The Avaya ASBCE, acting as a TLS server, sends its identity certificate to the peer device. The peer verification is grayed out because the endpoint does not send any separate identity cert to the Avaya ASBCE, so no CA authority is required. The verification depth is also grayed out. Click Next. To be compatible with other versions of TLS certificates, select the checkboxes for TLS 1.1 and TLS 1.0. The system default automatically selects TLS 1.2 only. Then click Finish. Relay services will be configured next. The ASBCE has to be configured to listen to the UDP ports that the media packets will be sending to the ASBCE. This service uses a default listen port range that has to be modified to allow other relay services, for example HTTPS, to use port numbers up to 9443. The new listen port range will begin at 9444 instead of 9000. To modify the listen port range, starting from the Avaya ASBCE dashboard, select Device-Specific Settings and then Advanced Options. Finally, click the Port Ranges tab located in the right pane. Change the default listening port from 9000 to 9444. Then click Save. To create a new relay service, starting from the Avaya ASBCE dashboard, select Device-Specific Settings and then DMZ Services and finally Relay Services. With the Application Relay tab selected, click Add. Create a new relay service. Give it a name like 1XP1, for example. Keep the service type as XMPP, which is set by default. Enter the remote IP FQDN address for the IP office server. For remote port number, use 5222. The remote transport is set to TCP by default. For the listen IP, use public B1 VLAN 0 and use the second IP address from the drop-down list. This is IP address that was set aside for remote worker external SIP trunk. Set the listen port number to 5222. For the connect IP, use private A1 VLAN 0. Use the second IP address from the drop-down list, which is the IP address that was set aside for remote worker internal SIP trunk. For the listen transport, leave it as the default of TCP. Click Finish. User agents such as Avaya 1X Mobile, Avaya Communicator, or Equinox are added so that different policies can be applied based on the remote device used to connect to the Avaya ASBCE. An Avaya Communicator remote worker uses SRTP, whereas 1X Mobile uses RTP. Navigate to Global Parameters and then click User Agents. Click Add to add a new user agent. In the Name field, enter Avaya 1X Mobile. In the Regular Expression field, enter Avaya 1X Mobile, period and asterisk. Note that you must enter both the period and the asterisk at the end of the expression. This is required by the 1X Mobile software. Click Finish. To create the second user agent, navigate to Global Parameters, then click User Agents again. Click Add to add a new user agent. In the Name field, enter Avaya Communicator. In the Regular Expression field, enter Avaya Flare, period and asterisk. Note that you must enter both the period and the asterisk at the end of this expression as well. This is required by the Avaya Communicator software. Click Finish. Signaling interfaces have to be created for the remote worker connections, including the internal remote worker as well as external remote worker. The port numbers and the protocols that will be used by the signaling interface are defined in this process. From the Avaya ASBCE dashboard, select Device-Specific Settings and then Signaling Interfaces. Click on Add in the right pane to add a new signaling interface. Type a name for the internal new signaling interface in the Name field. For example, enter SIG-RU Internal. This will be for the connections to the internal side of the network. RU is used to indicate the remote user for the enterprise connections. Set the IP address field to the new A1 or internal IP address. This is the IP address that we added for the remote worker internal SIP trunk. Set the TCP port and the UDP port to 5060, which is the default. For the TLS profile, leave as none. No TLS is required for worker internal SIP trunk. Enter SIG-RU Internal. This will be for the connections to the internal side of the network. RU is used to indicate the remote user for the enterprise connections. Set the IP address field to the new A1 or internal IP address. This is the IP address that we added for the remote worker internal SIP trunk. Set the TCP port and the UDP port to 5060, which is the default. For the TLS profile, leave as none. No TLS is required for internal interface connections. Shared control uses port 5063, which can be enabled to allow dual registration of the same user from two separate devices. Finally, click Finish. Now that the internal interface has been created, we need to create the external interface. Under Device-Specific Settings in the navigation pane, select Signaling Interfaces. Click on Add on the right pane to add a new signaling interface. Type a name, such as SIG-RU External, for the external new signaling interface in the Name field. This is for the connections to the external side of the network. RU is used to indicate the remote user. Set the IP address field to the new B1 or external interface. This is the IP address that we added for the remote worker external SIP trunk. Set the TCP port and UDP port to 5060, which are the default values. Set 5061 for TLS port. Select the TLS profile from the drop-down menu. Select the TLS server profile. Note, the external signaling interface does use the TLS profile for remote worker. Click Finish. Media interfaces, both internal and external, also need to be created for the remote user. This allows us to separate the remote worker traffic from the rest of the Avaya ASBCE traffic. From the Avaya ASBCE dashboard, select Device-Specific Settings and then Media Interface. Click on Add on the right pane to add a new media interface. The media interface allows us to define the port number that can be used by the voice and video traffic. Type a name for the internal new media interface in the Name field. For example, Med-RU Internal. This will be for the connections to the internal side of the network. RU is used to indicate the remote user. Note that this interface does not use TLS in the inside or private network. Set the IP address field to the new A1 internal interface. This is the new IP address that we set aside for remote worker internal SIP trunk. The port range is left unchanged and are set to the default values. Click Finish to complete the configuration. Now that the media interface internal has been created, we will now proceed to create it for the external interface. Within the Media Interfaces tab, click Add on the right pane to add a new media interface. Type a name for the external new media interface in the Name field, such as MED-RU External. This will be for the connections to the external side of the network. RU is used to indicate the remote user. Set the IP address field to the new B1 external IP address. This is the new IP address that we set aside for the remote worker external SIP trunk. Once again, the port range is left unchanged and are set to the default values. For the TLS profile, leave the setting as none. Note, the external media interface does not use the TLS profile. Click Finish to complete the configuration. In this video, we will configure the remote worker for the IP office. Remote workers require advanced sessions licenses for this feature. To create a new server profile for the call server, from the Avaya SBC dashboard, select Global Profile and then Server Configuration. Click Add in the right pane. Give the new profile a name, such as Call Server RU. Click Next. For the server type, select Call Server. For the SIP domain, enter the domain name where the Avaya SBC is located. For the IP address FQDN, enter the IP address of the call server, which in our example is IP Office Server Edition. Enter port 5061 and select TLS for transport. For the TLS client profile, select the TLS client. Note, the TLS client profile will not be enabled until the transport protocol TLS is selected. Then click Next. As no changes are required for the Add Server Profile authentication, click Next. Select the Enable Heartbeat checkbox and set the frequency to 30 seconds. This allows the SBC to know that the remote server or servers are up and running. In the From URI or Uniform Resource Identifier field, enter the FQDN name of the SBC. The Avaya SBC is the resource from where the SIP options originate. For the To URI field, enter the FQDN name of the IP office, which is the resource of the destination where the SIP options terminate or are sent to. This information is useful when debugging Wireshark traces. Then click Next. In the Add Server Configuration Profile ping, click Next. This allows the configuration of a ping to the external server at the interval that can be defined by the user. Select Enable Grooming. With grooming enabled, the system reuses the same connections for the same subscriber or port used by the TCP or TLS transport. Set the Interworking Profile field to the Call Server Interworking Profile. Leave the rest of the parameters as default values. Click Finish to complete the server configuration for the call server. The Routing Profile for the call server is next. This new call server routing profile uses TLS. From the navigation pane, select Global Profiles and then Routing. Click Add on the right pane. Give the new routing profile a name, for example, Call Server RP TLS. Remote workers will now communicate with the Avaya SBC using a TLS connection. Click Next. The Next Hop Priority checkbox is selected by default. Click Add to add a next hop address. Fill in the priority weight of 1. For server configuration, select the Call Server RU profile. The IP address of the IP Office Server Edition, along with the Transport Protocol TLS, is automatically selected. Click Finish to complete the routing profile. Media rules that use RTP or Real-Time Protocol or SRTP or Secure Real-Time Protocol for transporting the media for the remote workers now need to be configured. From the dashboard, select Domain Policies and then Media Rules. Select Default Low Med and then click Clone. Give the new media rule a name, such as Remote Worker RTP or Real-Time Protocol. In the Encryption tab, click Edit. Verify that the preferred format number 1 for audio and video encryption are set to RTP and that interworking is enabled. Click Finish. Create a second media rule for SRTP encryption. Select Default Low Med and click Clone. Give the new media rule a name, for example, Remote Worker SRTP for Secure Real-Time Protocol, and then click Finish. With the Remote Worker SRTP selected under Media Encryption tab, click Edit. For audio encryption preferred format number 1, select the SRTP AES 128-bit with SHA-1 with 80-bit hash algorithm from the drop-down menu. Set the auto encryption preferred format number 2 to RTP. For the video encryption preferred format number 1, select SRTP AES 128-bit with SHA-1 with 80-bit hash algorithm from the drop-down menu. Change the video encryption preferred format number 2 to RTP. Under Miscellaneous, enable Capability Negotiation. This option enables SIP and SDP or Session Data Protocol for the media signaling, which allows both Real-Time Protocol or RTP and Secure Real-Time Protocol or SRTP for media transmission. Click Finish to complete the media rule configuration. In this section, the Call Server Application rule is modified to include video sessions. This will allow both audio as well as video calls to the remote worker. In this section, we will also create a new Remote Worker Subscriber Application rule. Under System Management, select Domain Policies and then Application Rules. Select the Call Server AR and then click Edit. For the application type Video, enable both In and Out. In the Maximum Concurrent Sessions field, enter 500. In the Maximum Sessions per Endpoint field, enter 500. These fields are over-provisioned because some sessions take a while to clear. Next, create a new application rule for Remote Worker. Select the default subscriber low and then click Clone. Give the application rule a name like RUAR and click Finish. Select the RUAR rule we just created and click Edit. For the application type Audio and Video, enable both In and Out. In the Maximum Concurrent Sessions field, enter 500. In the Maximum Sessions per Endpoint field, enter 500. These fields are over-provisioned because some sessions take a while to clear. Click Finish. Next, configure the Endpoint Policy Group for RTP and then SRTP. The Avaya 1X Mobile and the Avaya Communicator use this encryption for the media packets. From the dashboard, select Domain Policies and then Endpoint Policy Group. Click Add in the right pane to add a new Endpoint Policy Group. Give the Endpoint Policy Group a descriptive name in the Clone Name field, such as RU Policy Group RTP, then click Next. For the application rule, select RUAR to indicate the Remote Worker Application rule. For the media rule, select the Remote Worker RTP created earlier from the drop-down menu. Leave the other parameters as default values. Click Finish to complete the Endpoint Policy Group configuration for remote workers. The Endpoint Policy Group Remote Worker allows us to put all the signaling rules together. create a new policy group for the SRTP encryption. Click Add on the right pane to add a new endpoint policy group. Give the endpoint policy group a descriptive name in the clone name field. For example, RU policy group SRTP, then click Next. For the application rule, select RUAR for the remote worker application rule. For the media rule, select the remote worker SRTP created earlier from the drop-down menu. Leave the other parameters as default values. Click Finish to complete the endpoint policy group configuration for remote workers. In the next configuration, we create the subscriber flows. A subscriber flow is the routing destination for traffic from the SIP endpoints. We will create one subscriber flow for 1X Mobile and another for the Avaya communicator. From the Avaya ASBCE dashboard, select Device-Specific Settings and then Endpoint Flows. Click Add in the right pane to create a new subscriber flow. Give the subscriber flow a descriptive name in the Flow Name field. For example, 1X Mobile. Leave the other parameters as default values, which are asterisks. Select the signaling interface from the drop-down menu. Choose the SIG RU External to select the interface used to communicate with the external remote workers or subscribers. Then click Next. Subscriber is selected by default for the source profile. The methods allowed before register are the additional SIP messages that can be used to register the remote workers. Use the Control key and hold to add more than one method. In our example, leave it as the default values. For the media interface, select the MED-RU external profile to talk to the external subscribers. For the endpoint policy group, select the RU policy group RTP created for remote workers that require RTP encryption. For the routing profile, select the call server RPTLS that is used for the outbound traffic using TLS. The TLS client profile uses the TLS client for remote workers. This setting is required for the present server, which we will set later in the screen. Note also that the Avaya ASBCE acts as a client when communicating with the remote workers. Hence, it uses the TLS client profile. Insert the IP address of the present server to indicate the present status of the remote workers. We will also create another subscriber flow for the endpoints that use the Avaya when communicating with the remote workers. Hence, it uses the TLS client profile. Insert the IP address of the present server to indicate the present status of the remote workers. We will also create another subscriber flow for the endpoints that use the Avaya communicator. Click Add to create a new subscriber flow. Give the subscriber flow a descriptive name in the Flow Name field. For example, enter Avaya Communicator. Leave the other parameters as the default values, which are asterisks. Select the signaling interface from the drop-down menu. Here, we need to use the SIG RU External to select the interface used to communicate with the external remote workers or subscribers. Then click Next. Leave Subscriber, which is the default for the source profile. For the media interface, select the MED-RU External to select the interface used to communicate with the external subscribers. For the endpoint policy group, select the RU policy group SRTP created for the Avaya communicator remote workers that require SRTP encryption. For the router profile, select the call server RPTLS that is used for the outbound traffic using TLS. The TLS client profile uses the TLS client for remote workers. This setting is required for the present server, which we will set later in this screen. Note also that the Avaya ASBCE acts as a client when communicating with the remote workers. Hence, it uses the TLS client profile. Insert the IP address of the present server for indicating the present status of the remote workers. Then click Finish. The last configuration required is the remote worker server flows for the call server. The server flow brings together all the profiles and rules. No server flow for the trunk server is required, as the remote workers connect directly to the Avaya SBC and not to the trunk server. A server flow is a routing destination sent by the call server. Click the Server Flows tab in the right pane and then click Add. Give the new call server flow a descriptive flow name, such as RU Call Server SIP Trunk Flow. For the call server configuration, select Call Server from the drop-down menu. For Received Interface, select SIG RU External. This is because the inbound traffic is received on the remote user external interface. For the signaling interface, select SIG RU Internal. For the media interface, select MED RU Internal. This is because the signaling and media packets are being received on the internal interface of the ASBCE. For the endpoint policy group, select Call Server Policy Group. For the routing profile, select Default. Recall that for call server, flow is set to default. In Topology Hiding Profile, select Call Server TH. Leave all the other fields as the default values. Click Finish to complete the remote user server flow for call server profile. This completes the remote worker configuration. Test by verifying that the remote worker can register to the ASBCE successfully will indicate the configuration is correct. The screen capture shows the IP address and the port that the Equinox will use to connect to the ASBCE. Calls should now be able to be made between the remote worker and the call server. The configurations of the call server and the trunk server are not a part of this course. You should now be able to list the requirement to configure the ASBCE for remote workers, verify advanced sessions licenses are installed, add new IP address for SIP trunk, install certificates, and create client and server profiles, create the signaling and media interfaces for internal and external users, add a new call server profile for remote workers, create the endpoint policy group, add a subscriber and server flows, test the remote worker configuration. This module focuses on optional features within the ASBCE that can be implemented in certain environments for a specific purpose or result. Some of the features may not be necessary in your environment, so it is not required to configure all of these options in your system. The objective provides a preview of what will be presented. By the end of this module, you should be able to explain the purpose of each of the following ASBCE features and complete the optional configurations for reverse proxy, multi-tenant, stun turn service, transcoding, transrating, media forking and SIP-REC, and finally, enhance and enable security features in the ASBCE. The first feature to discuss is reverse proxy. A reverse proxy is a web server that terminates connections with clients and makes new connections to the back-end servers on their behalf. A back-end server is defined as a server to which the reverse proxy makes a connection to fulfill the request from the client. These back-end servers can take various forms, and reverse proxy can be configured differently to handle each of them. A reverse proxy is also known as an inbound proxy because the server receives requests from the internet and forwards or proxies them to a small set of servers. The servers are usually located on an internal network and not directly accessible from outside. This proxy is reverse because a traditional or outbound proxy receives requests from a small set of clients on an internal network and forwards them to the Internet. The diagram illustrates the typical configuration of reverse proxy for file transfer servers. The reverse proxy is located behind the firewall, and the file transfer servers are often in the internal network. There are many advantages to using a reverse proxy. Here are just a few examples. Security is the first advantage. A reverse proxy hides the topology and characteristics of back-end servers by removing the need for direct Internet access to them. You can place your reverse proxy in an Internet-facing DMZ, but hide your web servers inside a non-public subnet. The reverse proxy also acts as a cache. You can either have a dumb cache that expires after a set period, or better still, a cache that respects cache control and expires headers. This option considerably reduces the load on the back-end servers. To reduce the bandwidth needed for individual requests, the reverse proxy decompresses incoming requests and compresses outgoing ones. This functionality reduces the load on the back-end servers that would otherwise have to compress outgoing requests. The reverse proxy also makes debugging requests to and responses from the back-end servers easier. Finally, access control is simplified. Clients only have a single point of access, so you can concentrate access control on that single point. To enable a reverse proxy, complete the following steps. First, log in to the ASBCE web interface with administrator credentials. Select the ASBCE device. In the navigation pane, click DMZ Services, then Relay, then Reverse Proxy Policy. Click Add to add a new policy. A new window with the Add Reverse Proxy Profile window appears. Provide data in the required fields. Refer to Administering the ASBCE Release 8.0 document for more information about creating a reverse proxy service for PPM traffic and for a file or firmware download. The Avaya SBCE achieves multi-tenancy using multiple IP addresses, or single IP address on a single or multiple data interfaces to service different users or groups. Each user or group of users is called a tenant that obtains SIP-based Unified Communications (UC) services via a service provider's ASBCE. Here is an example of a multi-tenant network using multiple IP addresses on a single interface. In this scenario, all the 4 ASBCE data interfaces are being used. The Avaya SBCE permits the use of multiple instances of the same or different IP addresses when the instances exist on separate network interfaces, virtual VLAN interfaces, or both. The ASBCE connects with 2 tenant networks, each with a unique set of remote workers. The A1 interface for tenant A uses VLAN 10 and 2 IP addresses, and the tenant B uses VLAN 20, also with 2 different IP addresses. ASBCE also connects to 3 other networks, each with a different call server. Each call server is reached through a separate physical interface, which provides a measure of redundancy when one or more call servers stop responding. We'll use that same diagram to explain the interface configuration. The A1 interface of ASBCE provides connectivity to tenant subnets using different IP addresses and VLANs for the tenants A and B. Tenant A in blue is on VLAN 10, while tenant B in orange uses VLAN 20. The gateway router on the A1 interface provides connectivity to both tenant VLANs. The B1, A2, and B1 interfaces provide connectivity to the call servers A, B, and C. Note, you can attach any of the tenants to any of the call servers A, B, or C through the A1 interface, which will provide the redundancy to the tenants. This network configuration supports corresponding mapping between ASBCE network interface cards, or NICs, and physical server NICs. Configure the gateway on the A1 interface to support VLAN, VLAN 20, and the associated IP addresses. You also need to configure the other three gateways on A2, B1, or B2 separately for each of the interfaces that connect to the call servers. The VLAN 10 has its tenant A IP addresses, also has to be configured. If the ASBCE is running on a virtual machine, configure VMware vSwitch and the physical interfaces on the server. If each physical interface on ASBCE uses a separate vSwitch and each vSwitch connects to a separate physical interface on the server, connect vSwitch to a physical port setup. Configure up to 4 vSwitches. Note, for detailed information regarding configuring multi-tenancy, refer to the document Working with a VIA Session Border Controller for Enterprise Release 8.0. Next, we'll look at an example that uses the same IP address to connect to the tenants A and B. The difference here is that each tenant connects to the ASBCE interface A1 using the same IP address, but a different VLAN. In the above example, tenant A is connecting to the ASBCE A1 interface using VLAN 10, while the tenant B connects to the A1 interface using VLAN 20. The A2 interface, as in the previous example, connects to the call server or servers as needed. The tenants A and B can connect to the call server using their respective VLANs 10 or 20. Here is an example of a tenant network using 2 different IP office servers for redundancy. These servers provide network access to the 2 tenants or remote workers. This example also includes a carrier SIP trunk to support PSTN access. The ASBCE uses different addresses on the B1 interface to support the carrier SIP trunk traffic to and from the tenant IP office clouds. For the tenant access, the ASBCE uses the same IP address and interfaces to support each tenant. This section presents the stun turn service. The stun turn service is needed to enable WebRTC and IP Office SIP trunks. WebRTC is an open-source project that seeks to embed real-time voice, text, and video communications in web browsers and mobile applications through simple APIs, JavaScript, and HTML5. STUN stands for Session Traversal Utilities for NAT. Refer to RFC 5389. Any SIP can use a mechanism called STUN to cross firewalls between the switch and the ITSP. This requires the ITSP to provide the IP address of their STUN server, or a public STUN server can be used. The system then selects from various STUN methods to connect to that server. The system then attempts to auto-detect the required settings to successfully connect. To use STUN, the line must be linked to the network topology settings of a LAN interface using the line's Use Network Topology Info setting. TURN stands for Traversal Using Relay NAT. It is a protocol that governs the reception of data over a TCP or UDP connection. TURN uses a single communication device operating behind a NAT or firewall. A TURN server relays packets from an IP address towards an internal device only if that internal device has previously sent a packet through the same TURN server to that particular external IP address. As mentioned previously, the STUN turn service is needed to enable WebRTC. An ASBCE can be used to secure and support incoming WebRTC calls to the IP office. The calls are routed via the WebRTC gateway service hosted on the IP Office Server Edition primary server or on an IP Office application server. WebRTC clients use the 9443 port for signaling and ports 56,000 through 58,000 or the default for media. These ports go towards the WebRTC gateway service on the IP Office Server Edition primary or IP Office application server. The main methods used to achieve this are an application relay for connections to port 9443 on the portal server, the use of STUN and TURN for media relay, and NAT resolution to the WebRTC gateway service on the portal server. Use the following process to configure STUN turn settings on the ASBCE to support WebRTC. On the ASBCE, select DMZ Services in the left navigation pane and then click Turn STUN Settings. Select the Add button to open this screen called the Add Turn STUN Profile screen. In the Listen port, enter the port on which the ASBCE should listen for STUN turn connections. The default is 3478. Ensure that the number entered matches the STUN server port set in the IP Office WebRTC Gateway Services Media Gateway settings. In the Media Relay port range field, enter the port range to be used for the turn server. This range should match the RTP port range public set in the IP Office WebRTC Gateway Services Media Gateway settings. Check authentication. This step displays several additional fields. Use these to set a required name and password for access to the turn services. Select the fingerprint checkbox. Select the protocols TCP and/or TLS that match those set in the IP Office WebRTC Gateway Services SIP server settings. Click Finish. The system displays the message at least one Listen Media Relay IP pair is required to complete the configuration. Click here to create a new pairing. To add the Turn STUN IP pairing, click on Turn Relay and then Add. A new window with the Add Turn STUN IP pairing will appear. Select the Add Listen Relay IP pair button and configure the network's Listen IP, Media Relay IP addresses through which data will pass, and the Turn STUN profile from the drop-down list for each of these configurations. Leave the service FQDN as blank. Once you update the fields in the ASBCE, configure the IP Office WebRTC Gateway service to enable turn support using the ASBCE. First, log into the server's web configuration menus and follow the path shown at the top of this screen. Then, select the Media Gateway Settings menu. In this screen, set the turn server details to match the turn service configured in the ASBCE. For example, enter the turn server address. The default is 0.0.0.0 disabled, which indicates the turn server is disabled or not used. The gateway service can use turn to attempt to resolve issues caused by network address translation or NAT applied to traffic between it and the external clients. Unlike stun, all traffic is routed via a turn server. The gateway attempts to use turn if a turn server address is set. The turn server port sets the port used for connection. In the turn username and turn password fields, enter the name and password of the account on the turn server if authentication is being used. Always remember to save any changes you make. This section defines transcoding and shows how to enable it within the ASBCE. To begin, let's define transcoding. Transcoding is needed when the inbound and outbound entities or devices have incompatible codecs. With transcoding, the ASBCE translates a media stream encoded by one codec into a media stream encoded by another codec. The SDP, or Session Description Protocol, offer contains information about preferred codecs by the device sending the message. The receiving device responds to the SDP offer by listing its supported codec set. Once a mismatch is detected, the ASBCE completes the translation. It is important to note that the ASBCE supports audio transcoding and transcoding for trunk deployments. Fax transcoding is not supported. All transcoded calls are anchored to the ASBCE. If a call has both audio and video M lines, the ASBCE only translates the audio. Video calls that require transcoding are converted to audio calls. By providing transcoding, the ASBCE optimizes bandwidth availability by enforcing the use of different compression codecs, normalizes traffic in the network to a single codec, and reduces the usage of multimedia resource function processors and media gateways to support a large number of codecs. Here is a list of the codecs that are supported by the ASBCE. From Release 7.2, an external Avaya Aura media server is supported, which allows for the number of transcoded media sessions to increase. Let's look at an example. This information was captured using Trace SBC. This screenshot shows the 488 code. If you reference the code list, a 488 code indicates there is a problem with the codec. In this instance, the call server or receiving device is not set to support that codec. Therefore, we need to enable transcoding in the ASBCE. To enable transcoding within the ASBCE, go to the Network and Flows option in the left navigation pane. Then, select Advanced Options and the Feature Control tab. In this tab, click the Transcoding checkbox. If the Avaya Aura media server offloading is required, click the AMS Offloading checkbox. Save to finish the configuration. To create a new media rule, click Domain Policies and then Media Rules. The existing media rules are displayed. The tabs to the right display the parameters for the selected media rule set. In the Applications pane, click Add. The system displays the media rule window. Enter a name for the new media rule, such as My Transcoding Rule, and the appropriate audio and video encryption information, and then click Next. In the Codec Prioritization screen, click the Codec Prioritization and Transcode checkboxes in the upper left. Then, select the transcodable codecs in the Available field. Move this codec over to the selected field using the right arrow. The letter T next to the codec indicates that it is transcodable when this feature is enabled. In the Video Codec section, the Transcode When Needed field is unchecked. Video codecs cannot be transcoded. To remove all codecs that are not included in the preferred codecs list, click the Allowed Preferred Codecs Only checkbox. This selection is optional. The next step is to add the media rule to the endpoint policy. In the left navigation pane, click Domain Policies and then Endpoint Policy Groups. The system displays the existing endpoint policy groups. Either edit an existing policy set or create a new group. In the Media Rule field, click the Transcode Enabled Media Rule. In this example, that rule is called My Transcoding Rule. Important: the endpoint policy group must be used by both the call server and the trunk server flows. If this is a new policy group, assign it to both server flows. In this example, we show the call server. Repeat the steps for the trunk server. Attach the endpoint policy group containing the transcode enabled media rule to the server flow. This ensures that the codec policy is applied for network messaging coming from or going to the server. In the navigation pane, under Network and Flows, click Endpoint Flows. After selecting device for which you want to change, click the Server Flow tab. In the row corresponding to the server flow that you want to change, click Edit. In this example, we'll edit the transcoding flow. In the Endpoint Policy Group field, click the Endpoint Policy Group with the Transcode Enabled Media Rule. Transrating reduces the bit or packetization rate of the media while retaining the original media format. It is required when the packetization period for the same codec is different between inbound and outbound streams. The packetization rate has a direct effect on the total amount of bandwidth needed and is useful where bandwidth is a constraint, such as on the Wide Area Network, WAN. Enabling transrating results in lesser number of packets and packet overhead because the packetization period is increased. Therefore, efficient media delivery within a reduced bandwidth is possible. For example, the packetization period, or P time, is 40 milliseconds on the WAN and 20 milliseconds on the internal enterprise network. They both use the same codec. For this example, transrating is required because packetization period for the same codec is different between inbound and outbound streams. To continue, the ASBCE supports transrating for audio sessions for calls traversing the ASBCE for SIP trunking. The packetization period, or P time, is negotiated through SDP signaling. ASBCE also supports symmetric transrating, which occurs when the far-end device sends P time that is the same as the offered value or a value that is less. The ASBCE selects the P time value from the answer as the packetization period. Symmetric transrating is used for both the RX and TX streams. Navigate to Network and Flows, then Advanced Options and Feature Control. To enable or disable transrating, select the Transrating checkbox in the Feature Control tab. Then click Save. To set the code prioritization within the media rule, navigate to Codec Prioritization. Then click on Edit to edit the codec prioritization. Enable the codec prioritization and transrating by clicking on the checkboxes. Then, select the transrating codecs in the available field. Select the p-time 30. Move the codec over to the selected field using the right arrow. Remember the letter T next to the codec indicates that it is transcodable. In this example, transcoding is not enabled, so it will not be enabled for this codec. As we did with transcoding, the next step is to add the media rule to the endpoint policy. Either edit an existing policy set or create a new group. In the media rule field, click the transrating media rule. In this example, that rule is called My Transrating Rule. Again, it is important to note that this is the same endpoint policy group currently used by both call server and trunk server flows. If this is a new policy group, it needs to be assigned to a respective server flow. The final feature covers media forking and SIP-REC. The ASBCE delivers a capability for media stream replication on incoming audio sessions, such that the stream can be forked and simultaneously sent to both the clients and to a separate IP address. This second IP address can be a recording device. In general, the call recorder is connected to the IP PBX through a CTI, such as Application Enablement Services. This setup allows the transfer of call and endpoint information from the IP PBX to the call recorder through a proprietary interface, for example, JTAPI. To create a media forking profile, from the dashboard, click on Configuration Profiles and then Media Forking. Give the media forking profile a name and click Next. A new media forking profile window will appear. The media forking feature allows the ASBCE device to fork media packets according to a designated media forking profile. The media forking profile contains parameters for sending a duplicate stream of media packets to a call recorder. Media forking is mirroring all information on L3 and onwards. Mirroring is necessary so that a copy of the packets are sent and captured in the recording server. The source MAC is that of the ASBCE port to be mirrored, and the destination MAC is that of the recording server. Let's spend more time on the media forking profile screen. In the Call Scenario section, designate the type of call to be forked. In the Media Type section, select the part of the call to mirror. The Mirror RTCP stream field designates whether to mirror the RTCP or Real-Time Transport Control Protocol stream. In the Ethernet interface, specify the interface. If you are enabling Enable VLAN tagging to identify which VLAN the packets belong to, select the checkbox and specify a VLAN ID and a protocol. For destination and source MAC fields, enter the correct MAC address. Then select Media Anchoring and the correct profile. Click Finish to save your changes. Finally, in the Add Flow screen, change the name of the session policy to the name you created earlier. Note that the media forking can only be added to the session flow and not to an endpoint flow. Let's transition from media forking to SIPREC. Session Initiation Protocol Recording, or SIPREC for short, defines the architecture, associated call flows, and metadata that can be used for call recording. SIPREC identifies two players involved in call recording: the Session Recording Client, SRC, and the Session Recording Server, SRS. Although SIPREC doesn't limit the SRC and SRS to specific entity types, for the purposes of trunk-side recording, it is safe to say that the SRC is an SBC and the SRS is a call recording platform, such as NICE. ASBCE Release 7.0 and higher support the SIP-based media recording standard, which is called SIPREC RFC 6341. Third-party call recording solutions that implement the SIPREC standard and can record calls that traverse the ASBCE using the ASBCE as the SIP recording client. The recording servers can be co-located with the ASBCE or distributed in different locations. If the SRS and ASBCE are at different locations, ensure that the network does not require network address translation, or NAT, between the SRS and ASBCE devices. Two types of recording are supported. Selective recording begins recording and media streaming when the recorder indicates to ASBCE to start streaming. This recording type conserves bandwidth. On the other hand, continuous recording occurs when the secondary recorder joins seamlessly to the ASBCE. This option provides load sharing or failover of primary recorder. To understand the recording feature, it is important to understand how the ASBCE interacts with the recording servers. First, the ASBCE supports major third-party SIPREC recorders. In addition, if the ASBCE is to communicate with a cluster of recording servers, administer a URL for each recording server in the cluster. There are no new SIP message types to support SIPREC. SIPREC utilizes common messages such as invite and buy. However, the big change lies within the message body of those invite and buy messages. The ASBCE sends an invite message to the recording server. When ASBCE sends the contact URI in the invite message with the feature tag of +sip.src in the invite message to the SRS identifies a recording session. As expected with all SIP call flows, SDP, or Session Description Protocol, describes the session's media. For example, the G.711 or G.729 codecs. In addition to SDP, the message body of a SIPREC invite contains a second part. In SIP parlance, this is known as a multi-part MIM message body. The first part of the message body is SDP, and the second part contains SIPREC metadata. This metadata is used to convey information that is specific to the process of call recording. The metadata of a SIPREC invite is formatted as XML data. The table shows the metadata elements the ASBCE provides to the SRS. ASBCE supports SIPREC with transcoding when the main call is transcoded. ASBCE does not support transcoding to the recorder in this release. Ensure that G729AB with G711 codec is configured on both sides of the media rules. However, transcoding can happen with different codecs. Here is a list of all the steps necessary to configure the ASBCE for SIPREC. The following slides will show how to complete these steps. Since these steps were covered earlier in the course for other configurations, this section provides an overview of each step. To add a recording server, navigate to the SIP server configuration link. Add a new server and give it a new name. In the server type field, select Recording Server. In the IP address FQDN section, complete all these fields. The IP address entered is for the recording server. Important: each call that is recorded using SIPREC will require 2 standard session licenses and 1 advanced session license. Next, add a routing profile for the recording server. Click the configuration profiles, then Routing link, and click Add to create a new profile. Name the new profile. In the profile screen, complete the required fields. At the bottom of the screen, the IP address entered is for the recording server. To enable a UCID or Universal Call ID for the signaling rules, use the Signaling Rules link to navigate to the UCID tab. Then click Edit to enable the functionality. Complete the signaling rule screen and enable the signaling rule. Note, the node ID is a unique 2-byte network node identifier that is assigned to the ASBCE device. Every entity that generates a UCID has a node ID. The node ID must be unique across a solution. To create a new policy group for the recording server, navigate to the Endpoint Policy Groups, add a new group name, and complete the policy group or Edit Policy Set screen. Notice the signaling rule should be the recording signaling rule. Next, create a new session policy for the recording server. Use the Session Policies link to add a new media rule. Be sure to check the Media Anchoring and Recorder Server checkboxes. In the Recording Type field, select Full-Time or Selective. In the Routing Profile field, select the routing profile the ASBCE uses for the recording server. Now that we have a session policy, create a session flow. Use the Session Flows link to access and add session flows. Complete the Add Flow screen. In the URI Group Number 1 and URI Group Number 2 field, select the URI group policy to identify the source or destination of the call. You can use the URI Group Number 1 and URI Group Number 2 fields to restrict the calls that ASBCE records. For recording all calls, leave the default value of the asterisk in the URI Group Number 1 and URI Group Number 2 fields. In the Subnet Number 1 and Subnet Number 2 fields, type the subnet addresses. You can specify the source and destination subnet addresses in the Subnet Number 1 and Subnet Number 2 fields. For recording all calls, leave the default value of the asterisk in the Subnet Number 1 and Subnet Number 2 fields. Just like a call server and a trunk server, a recording server requires server flows. Use the Endpoint Flows link to navigate to the Server Flows tab. Then, add one new server flow to start. For the recording server, create an inbound and a separate outbound recording flow. This concludes the summary of the configuration for SIPREC. Let's look at how we can enable and enhance the security features in the ASBCE. The ASBCE uses a multi-layer hardening strategy to prevent security violations and attacks. The strategies include securing by design, securing by default, and securing the communication traffic between the ASBCE and the remote servers or workers. It is designed to be resilient to attacks that may cause malfunction or theft of service. Secure by design encompasses a secure deployment strategy that separates management configuration and traffic from the rest of the network traffic in or out of the ASBCE. The architecture allows the complete separation of the management traffic from the user traffic. This also separates the private and public networks, separating them into zones so that they accommodate only the traffic they have been designed for. The Unix operating system provides hardening by default by incorporating inherent security features built into it. In this way, it can provide mission-critical call processing applications and protect the customer from toll fraud and other malicious attacks. The hardened limits for the number of access ports, services, and executables protect the system from typical modes of attack. Using TLS SRTP encryption methods for the signaling and media traffic allows control on device type and users that are allowed through the ASBCE. Criteria used for admission control include source subnet, user agent, and URI group, which can be used to control things like device type and/or users that are allowed through the ASBCE. With the unsurpassed growth in the number of devices available for users, the level of attacks to the networks has equally spiraled. As with any system, the number of users that will be accessing the system will determine the number of errors that can be allowed. Most common attacks are designed to deny service to that device or devices. The attacks could come as a single source or as continuous phone calls, low-volume stealth, and call walking. All of the DOS attacks have default configurations that have to be modified to fit the traffic needs of the customer. Protocol scrubbing packages are available to detect anomalies in the messages. Using encryption and secure protocols for the media and signaling traffic prevents the information from being intercepted and accessed. Remote workers that require access to the ASBCE can use TLS certificates to prevent unauthorized access. Denial of service and distributed denial of service are the most common attacks on voice and data networks. The known types of attacks are single-source DOS, phone DOS, stealth DOS, and call-walking DOS. To prevent these attacks, it is necessary to change the threshold values for the number of SIP messages and the time interval during which these messages are received. Depending on the type of attack, the default number of the messages and the time have to be modified. Also, the default action of each needs to be changed from alert to block. It is recommended that based on the traffic, these values need to be tuned to avoid false positives, negatives. Protocol scrubbing is an ASBCE feature that utilizes a highly sophisticated statistical mechanism to thoroughly check incoming SIP signaling messages for various types of protocol-specific events and anomalies. It verifies certain message characteristics, such as proper message formatting, message sequence, field length, and content against updatable templates received from Avaya. Typically, messages which violate the security rules dictated by the scrubber templates will be dropped, while those which violate syntax rules will be repaired, either rewritten, truncated, rejected, or dropped, depending upon the processing rules imposed by the templates. To enable DOS feature for the ASBCE, go to Device-Specific Settings. Next, Advanced Options, and then Feature Control on the right pane. Select the Single Source DOS Protection feature, for example, and then click Save. To configure Single Source DOS thresholds, go to Global Parameters, next DOS, DDoS, and then Single Source DOS. Click on Edit. The threshold value should be changed to 20 SIP messages per 5 seconds and the action of block if this number is exceeded. The block duration can be configured to the number of seconds desired. It is set to 5 seconds by default. Refer to the security guide for the settings of the other types of DOS and DDoS attacks. To configure Protocol Scrubber, go to Domain Policies. Next, Security Rules, then Scrubber. Click on Add to add a new Scrubber rule. Select the package desired and click Finish. Click on Enable to enable the Scrubber package. See the table next to view the options offered by the different packages. Different packages are available for trunk configurations, as well as remote worker configurations. Review the features of each package to apply to the needs of the customer traffic. Encryption can reduce the risk of intercepting phone conversations, voicemail, and the SIP messages that support them both. A call generally consists of voice RTP data and SIP signaling messages. Both media and signaling data can pass through many devices and networks, sometimes over a separate network or virtual path from each other. Without encrypting, both data types are susceptible to either spoofing or eavesdropping, so anyone with access could intercept RTP in phone calls and voicemail and SIP messages. Refer to the table for the details of how to mitigate vulnerabilities in SIP and RTP. ASBCE uses the Transport Layer Security (TLS) protocol as a transport protocol for encrypting SIP messages to prevent tampering of communications sent across a network. ASBCE supports SRTP for encrypting the media traffic to prevent eavesdropping. To secure the remote access of files for the configuration of phones and the SIP setting for the remote worker, it is recommended to use HTTPS for communication. Use of TLS certificates for authentication prevents unauthorized access to the settings and firmware files. Review the phone documentation to ensure that TLS authentication is supported. For remote workers, the recommended configuration is to use HTTPS proxy for firmware downloads and settings file. Do not use relay service. For the phone staging, if authentication is required, it can be done in 2 stages. First, the certificates should be downloaded internally using HTTP. That way, the phones can be ready for remote deployment. The ports list is useful in understanding all the port numbers that are used by the management interface of the ASBCE. These ports have to be configured to be allowed on the firewalls for the services to operate. The ports list is useful in understanding all of the port numbers that are used by the A1, A2, B1, and B2 ports of the ASBCE. These ports have to be configured to be allowed on the firewalls for the services to operate. The ports list is useful in understanding all of the port numbers that are used by the A1, A2, B1, and B2 ports of the ASBCE. These ports have to be configured to be allowed on the firewalls for the services to operate. Now, we are at the module summary. In this module, you learned how to explain the purpose of each of the following ASBCE features and complete the optional configurations for reverse proxy, multi-tenant, stun turn service, transcoding, transrating, media forking and SIPREC, and enhance and enable security features in the ASBCE. In this module, we will look at the different options for administering and troubleshooting the SBC. After completing this module, you will be able to view system logs and audit logs, run diagnostics tool and ping, create backup and restore the system, create automatic and configurable snapshots, view alarms, incidents, and generate incident reports, enable and enhance the security features in the SBC, use Trace SBC to monitor traffic and troubleshoot connections and calls. The Element Management System provides a web interface to view logs and reports. The syslog can be accessed from the menu on top of the Avaya SBCE dashboard. Click on Logs, then System Logs. The different options for the class include Platform, Trace, Security, Protocol, Incident, Registrations, Audit, GUI, and Unknown. The different types of severity include Unknown, Info, Notice, Warning, Error, Critical, Alert, and Emergency. Other filtering options also include Start Date, End Date, Start Time, and End Time. Also, you may use the filter of a keyword search. Clicking on any item in the syslog opens up the syslog details window, which provides details regarding the log. Here, the time, the device name or host, the process that generated the log file, the severity of the log, class, and the module that generated the log file are displayed. The message section provides additional information regarding the message. Audit logs record every action that is taken by the administrator on the SBC system. The audit log tracks every security-related events, such as logins, session starts, session ends, new user additions, and password attempts, retries, and changes from the time a user logs in into the SBC system. The logs can be filtered using start date and end date fields. View the details of each log by double-clicking on a particular log. The details are shown in a new window. Set the log level by entering the dashboard, then clicking Device-Specific Settings, and then Syslog Management. The window allows the selection of the log level and the class of logs that will be collected by the system. The Collectors tab displays the location of the logs. Note that log local 5 and log local 6 cannot be modified since they are used for audit logging. The Avaya ASBCE diagnostic tool provides the ability to do a full diagnostics by pinging all the EMS and SBC A1 and B1 interfaces. To run the full diagnostics, click on the Start Diagnostic menu option. Then click the Start Diagnostic button. The system pings the different interfaces and gives the average ping time to reach that interface. Note that the internal or private IP address is not reachable from the external or public interface. From the Diagnostics window in the Ping Test tab, you can also ping at any destination IP address from any of the source interfaces of the Avaya ASBCE, including the management interface and the private and public interfaces. Select the source device or interface, enter the destination IP addresses, and click Ping. If the destination is reachable, it indicates the time to reach the destination. If not, it indicates that there was an error attempting to reach the destination IP or server. In this video, we will look at snapshots, backing up and restoring the SBC. The Backup Restore feature provides the ability to back up or create a snapshot of the EMS configuration to a user-definable external SFTP or Secure File Transfer Protocol server or to a local EMS server. You can download the snapshot to your local desktop using the download link provided in the Snapshot tab. The backups can be done directly from the graphic user interface of the Element Management System or using the command line interface. The snapshots can only be restored to the same EMS or SBC. If the hardware and/or software versions do not match, the restore will fail and the SBC will revert to its previous configuration. Configuration of backups can be done manually or enabled automatically to take periodic snapshots. It is important to note that since a snapshot contains information such as certificates and keys, which can be misused to gain unauthorized access to the SBC server, the administrator must ensure that the storage directory on the remote server is accessible only to authorized users. To create a snapshot of the current configuration, from the dashboard, select Backup Restore. Next, click Snapshots, and then select Create Snapshot. Give the snapshot a descriptive name. Click Create. Upon successful creation, a message indicates that the snapshot generation was successful. Note that the version of the server is included with the snapshot name. Snapshots can be stored locally on the EMS or can be downloaded to an external location. Select the snapshot file you wish to download and then click Download. The system automatically creates the backup file as a compressed zipped folder. To restore the snapshot, either from the local EMS or an external location, start from the dashboard. Click on Backup Restore. If the file is located on the local EMS, select the file you want to restore first, then click on Restore, located to the right of the file. A Restore Snapshot warning window gives information that the hardware and the IP address have to be the same, and the devices must be in a commissioned state. Click on Start Restore to begin the restoration. Note that restoring a snapshot does take a few minutes. Upon successful restore, the system sends the Snapshot Restoration Successful message. Click on Finish. To restore from a file located in the local desktop or external location, select the Restore by File button located above and to the right of the file name. Here, the steps show how the restore by file is done. However, we will not do the actual process. Click Cancel after the selection of the file, since we will not complete this process at this time. To create an automatic snapshot, click on Automatic Snapshot Configuration. In the example, a backup will be created every week on Sunday at 11 a.m. For the configuration of the automatic snapshot, select Weekly. Select the time to 11 a.m. using the 24-hour clock. Select the day or days for the automatic backup, such as Sunday. Click Save to save the automatic snapshot configuration. A green bar indicates that the automatic snapshot has been successfully saved. We will next look at configurable snapshots. Configurable snapshots allows one to create copies of the configuration that can be used to create a new system. Before a system can be restored using portable snapshots, there are a few steps that need to be taken to assure a successful migration. The new ASBCE device or devices, in the case of HA systems, should be in the commissioned state. The new ASBCEs should have the identical characteristics of the original ASBCE system. Hardware characteristics, that is, the same number of interfaces. Software characteristics, that is, the same version of the software as well as the VM resources. The IP address of the new EMS must also be the same as the IP address of the original ASBCE. Once the snapshot has been restored to the new system, the certificates have to be synced manually. To create a configurable snapshot, select the Configurable Snapshot tab and then Create Configurable Snapshot. From the device list, select the ASBCE device of which a snapshot is to be created and provide a name for this snapshot. Click Create. On successful creation of the snapshot, the success message displays. Once the snapshot has been created, it can be downloaded to the local drive. The name format for the snapshot file is name, date, version.back. To restore an existing configurable snapshot, click Restore. Select the name of the new ASBCE device from the drop-down menu onto which the configurable snapshot will be installed. We will not perform this since it requires additional SBC server. The steps show the procedure for restoration, although it has to be done on different server. Cancel out to exit out of the restore. Since we are not completing these steps in existing configurable snapshot, click Restore. Select the name of the new ASBCE device from the drop-down menu onto which the configurable snapshot will be installed. We will not perform this since it requires additional SBC server. The steps show the procedure for restoration, although it has to be done on different server. Cancel out to exit out of the restore since we are not completing these steps in our example. In this video, we will look at incidents, alarms, and reports. When we log into the EMS dashboard, the toolbar displays the number of currently active alarms for the selected ASBCE device. Clicking on any of the alarms opens the Alarm Viewer screen that displays the alarms that have occurred on that device. It gives the details about the alarm, including the time and the device on which the alarm occurred. Here we have the option to clear the alarms individually or all the alarms. The system incidents can be viewed directly from the GUI menu bar on top of the dashboard of the EMS. Clicking on Incidents opens a new screen with all the options for viewing incidents. The viewing options include the devices that you want to view, the category of the incident, and also the option to generate a report of the incidents. Every incident that occurs in the system is logged in the incident viewer, which contains the details pertaining to that incident. Since the list of incidents is considerably large, find more information in the Avaya ASBCE Troubleshooting and Maintenance Guide. Clicking on any incident opens up a new Incident Information screen with the details of that incident. These details include the type of incident, the date and time of the incident, category of the incident, device associated, and the cause of the incident. Depending on the type of incident, additional information, such as the transport protocol, the source from where the incident was generated, the destination IP addresses, and the server configuration display in the message window. Some incidents do not have any additional data. They only display the general information. Incident reports may be generated and downloaded for review and analysis if needed. Select the device and category and then click Generate Report. Enter the start date and the end date for which the report is desired. Click Finish. An Adobe PDF format incident report file is generated that can be saved to the local drive. The file provides a chart of the number of incident report with the date that the incidents occurred and a table of all the incidents that occurred during the selected date range. In this video, we will look at Trace SBC. For demo purposes, a call between the IP office and the communication server will be made to view the SIP traffic of a live call. On one desktop, we have the Avaya communicator connected to the IP office at extension 1026. And on another desktop, we have Avaya 1X Mobile connected to the communication server at extension 8023. Use an application such as PuTTY to log in to the ASBCE. Log in using root privileges, using the su root command and password. Press S to start the tracing. In the Start Capture screen, select the SIP protocol and the SIP handshake to view all the steps for the SIP conversations as well as the SIP handshake steps. The call is made and the traces can be viewed in live mode. When a call is made, the SIP message 100 trying and 180 ringing display. Accept the call on the second desktop and view the messages that the extension 1026 has been connected between the two IP addresses, the communication server with IP ending in .71 and the IP office with the IP address ending in .86, using the TCP port 5060. Disconnect the call and see the traffic when the call terminates. The SIP message BYE is sent to disconnect the call. Note that the maximum number of packets captured is only 10,000. Type S again to stop the tracing. The ladder diagram displays the messages that were captured by the trace. Select SIP and press Enter on your keyboard. Use the arrow keys to navigate through the SIP messages. Shown here is a trace of a real-time SIP call. Using the arrow keys, it is possible to scroll up or down to a particular message and look at the details of each message. For example, we can scroll up to look at the invite message, which was originated from the ASBCE to the external SIP provider. SIP invite messages are important because this is the first step in establishing communication between two endpoints. With the invite selected, we can hit Enter and the details of the invite message display. The header of a message detail form shows the source and destination IP, source and destination port, and the transport protocol used for the transport. TCP port 5060. This allows the troubleshooting of the source, destination IP addresses, and protocols used for the SIP communication. This way, we can move up and down the trace to view all the SIP headers. Filters can be used to view specific information. Filter calls that contain URI number in the from and to field. Filter messages from to IP address. Filter on the SIP call ID header. Filter messages based on regular expression. Filter on the SIP AV Global Session ID header. Filter SIP header field and value. Filter using logic operations. You should now be able to view system logs and audit logs, run diagnostics tool and ping, create backup and restore the system, create automatic and configurable snapshots, view alarms, incidents, and generate incident reports, enable and enhance the security features in the SBC, use Trace SBC to monitor traffic and troubleshoot connections and calls. In this course, we covered following topics: